Welcome back to the stream, everyone. There's Tuco. He was in the hallway, but now he's exploring the rest of his food. So welcome back. This is another Senrio Labs stream. We're going to be working on two projects. There's sort of the ongoing voltage glitching effort to try to get some firmware out of this PLC that mostly just wants to talk to us over Ethernet. Then we've also got this other instance of that same PLC, which we've been trying to get in through a different route, through what appears to be a bootloader. It looks like, well, so just to recap a little bit, the reason we are currently working on two has to do with the bricking. So we have this one PLC up here. Actually, while I'm trying to actually give some context for this project, maybe I'll actually bring out the actual PLC hardware here. I mean, that is the actual hardware, but you can't quite tell what it is when it's just a pile of circuit boards. Normally it fits in this housing. This is an industrial controller that would be running all sorts of things, from pay toilets to breweries. And basically anytime you need to connect a bunch of motors and switches and relays and sensors together in an industrial setting, you'd use something kind of like this. And a lot of these now have Ethernet connections, which they use for talking to each other and for programming. And we also have, just also noticing that folks are already starting to show up in chat. Hello, everyone. And yeah, there's a new chat system. So anybody who's used the YouTube or the very few people who had used the Twitch chats in the past, both of those have now been pretty much replaced with this Gitter chat, which the main advantage we have there is that it's easy for us to carry on conversations even between streams, which seemed pretty handy. And it also ties in pretty well with development efforts that we're doing here, so we can easily kind of go between this channel and channels related to the other projects we have on GitHub, including the cat robot or the glitching tools or anything else that we're working on. So, yeah, slight stream meta distraction there. But yeah, overall view is we have the guts of two of these PLCs, which are basically industrial Arduinos. It's right there and there. This one is currently running a voltage glitching experiment where I am hitting it with very targeted little power spike during the time when it's processing an HTTP request. So, the idea behind this is that it's going to have a little web server running somewhere in its firmware. And that web server will be, it'll be doing a bunch of things to get the HTTP response ready in between that last packet of the request and the first packet of the response. So we've targeted that particular range of time, which is just a few milliseconds in this case. And we're trying to find both, how do we line up this range of processing on the CPU with all of our external equipment. So that was this kind of side effort to get a stable trigger. Then after that trigger point, we can kind of step through this range of time and try to figure out where interesting bits of code are relative to the trigger. So that's what's going on up here. And in fact, oops. Looking for the Osclope, and now I'm already forgetting where the Osclope is. That's kind of what I want. There we go. So, yeah. I think Tuco already went back outside. So here in the Osclope, you can see this experiment up here running. And so this is something we've been looking at for a while. There are a couple of changes since the last time, if you've seen this before. Basically, the oscilloscope is showing us the events that bracket this region of time that we're interested in. So that digital trace D4, do I have a pointing device? Yeah, there's this PLC, we were trying to hit it with voltage glitches between the HTTP GET request and the response that it ends up having. Hey, Tuco. Welcome to the desk. Tuco was chilling out before and just like napping nearby, which would have been a great time for a stream, and now he's like more active since he finished his nap. Hey, buddy. So Tuco's sitting in front of the scope. Let's see if I can still operate this. There's a little bit of mouse lag when I move the scope mouse around on this screen. Anyway, so on the scope you have this big red trace, which is our power side channel. So that's how we're mostly taking a peek at what the CPU might be doing behind the scenes without any other I/O activity that we can see. So in this case, you can kind of use it to see how well the glitch is lining up, and you can also use it to kind of see the different phases of processing that might be going on, and how this request's processing lines up with the main loop in the background. So if I zoom out a little bit, you can see the structure of the main loop in the firmware. So it varies a little bit. It probably has events that it responds to and periodic timers that it takes care of, and there are also some other Ethernet packets going on. So D4 and D3 are the Ethernet transmit and receive. So D4 is a packet going from our experiment through this Raspberry Pi into the device under test, this PLC. And then D3 is the opposite. That's the PLC responding over Ethernet. And these are both nominally 10 base T Ethernet, but we've underclocked the entire experiment by about 25%. So these are actually going to be kind of weird underclocked 10 base T Ethernet signals that are not really standard. So that's why we have another one of those microcontrollers with the same underclock acting as the peer. So this is just another request and reply that came as probably the connection establishment. That was probably just like TCP SYN or something. And then we have these other two packets. This is the one that the Raspberry Pi, before it sent it, noticed that it contains the GET request that we're looking for. So D1 here is the result of a string match in the Raspberry Pi that gives us some advance warning that the next packet is going to be interesting. Then D0 is the trigger generated by this little add-on FPGA on the experiment. So that's just taking the kind of advanced warning from the Raspberry Pi and then the actual Ethernet packet, and then as a third triggering step, then finally lining it up to one of these edges on the clock output that our PLC is, the PLC program is giving us once per main loop iteration. So the goal of this whole thing is to give us a trigger, which we're seeing on D0, that goes high right at the last main loop edge before that gap. So you can see it doesn't always work. Sometimes another event comes in and kind of screws this up. Sometimes the packet just doesn't quite line up right, and we end up guessing the wrong clock edge, like right there. But mostly it works. And given that I'm trying all the experiments multiple times, it's enough, enough of these are going to be correct that it should be decent, at least for testing this space and testing to see if there are any interesting glitches within this space, within the parameters that we already have set up for the actual shape of the glitch pulse. So, oh, nice. Looks like Piotr in chat is happy with how I set up the chat window. Yeah, I'm glad that this is working out. I've got these in pretty much I think every one of my little channels here has an associated chat window. So, and I have this little one for the kind of opening cards. So, where was I? I think I was over here on the Oscoscope. I'm always forgetting where that Oscoscope is. Here it is, top O. You'd think that I would remember it, because it actually kind of makes sense. So what this is doing, so you can see that big spike is our power glitch. It actually doesn't quite look right to go. It doesn't quite look right on that trace on account of, ow, ow. Ooh, that was sharp. Hey, Tuke. That's what I get for putting the cat on my back. So this red trace is coming from a low noise amplifier board. That's the one that we soldered directly onto the back of the board. Then I've also got the blue and the yellow probes, which I'm about to turn on. I'll make the red one a little smaller so we can see. So this is still a very broad view. To actually really get a sense of what's going on with the glitch, we're going to need to zoom way into the actual glitch pulse. So now we're starting to see, and I'm going to need to back this way off. So the red and the blue traces should be basically the same, just with an amplification factor. So the upshot of what's going on here is that the blue trace is a passive oscilloscope probe. That's the 10x probe right here. And the red trace is a 50 ohm cable going off to this low noise amplifier board, which is then connected directly to where the decoupling capacitors usually would go on the core voltage rail with some a short length of thick twisted pair magnet wire. So I think what I've got is that the amplifier is actually really good for showing me the small details in the power trace, since that's actually letting me, like, I can zoom into much smaller details there just on account of the vertical resolution of the scope. So like with that blue trace, if I was trying to really zoom in and see the structure of the main loop, for example, you know, I can get down to 10 millivolts per division, but that's as far as I can go because the scope goes to 1 millivolt per division and it's a 10x probe. So, but if I start zooming in on the red trace, just because of the gain that I've got on that local amplifier and because I'm not using a 10x attenuation in the, you know, in the probe, like I can zoom in pretty much as I want on that signal. So that's why I'm using the amplifier mostly. It's mostly just for the gain. But let's see. I don't see these quite perfectly track at this time scale, but well, that's interesting. Yeah, those two signals are definitely not tracking each other as well as I would have thought at this kind of time scale. So I guess what I'm getting at is the red trace is higher amplitude. The blue trace is probably more accurate, but mostly what I can say is that they're different. And especially if you look at where the glitch is just starting and you try to get the amplitude and the general bias levels to match between these two traces. So separate these a little more so they're easier to see, but now you can see that at this time scale, the trace with the amplifier is looking a lot worse. So now that we're looking at these really wide swings that occur at the less than 10 nanosecond kind of scale, now the very first glitch pulse seems to be represented all right, but then the subsequent glitches, I was trying to figure out what this phenomenon might have been. Like, it almost looks like it looked a little bit like the amplifier was just like running out of power, like maybe the capacitor in the bias T was discharging or something. And then I'm forgetting who, but someone else mentioned on Twitter afterwards that this might also occur if the capacitor, like the AC coupling capacitor on the amplifier's input is charging up, which could also make sense. And they suggested adding a high-value resistor from the amp input to ground, which might work, although I think right now I'm fairly happy to just use these two signals for different purposes and to use the scope probe directly for the really wide swing stuff like the glitch, and to use the low noise amplifier for the stuff where I just want more gain. But this does mean that maybe I have some more opportunity to have a better amplifier in this and get better results. So this is just going to keep going. It's actually going a little slower than it usually goes right now because I think this is still another diversion, but I think Chip Whisperer might have a memory leak such that, or it might not even be a memory leak. It might just be that when it's adding the results to the results table. So if we take a look at the software that's actually running this right now, I've got Chip Whisperer. It's sending all of these. It's requesting just the CSS actually. So like if I were to issue the same thing over here, so that's the network proxy. Here's just another command line. So you can see the scope triggers when I do that, because that's actually, like the Raspberry Pi is looking for that particular HTTP GET, and that's actually causing the FPGA to trigger. But yeah, if the glitcher is not armed, then I won't get the same glitch result. But if I back up enough that you can see the actual experiment again, and go way into this power trace. This far away, the glitch looks really small. So if I just do a curl, then you can see the glitch doesn't happen because the glitcher isn't armed, but I'm still triggering the scope the same way. Sometimes this gets stuck if I do it when the processor is not actually in a position to respond. But yeah, I think this is just the UI data table filling up, which there's so many ways to fix. I've been on the verge of jumping ship from the Chip Whisperer UI to something else on this project for a while now, and this might be the last straw. So let me just stop this and then check this to see if anything is interesting in here yet, and assuming not, I'll just start the experiment again with a different starting point. So I'm just sorting these by the actual text that it received. And all of these are either failures or the exact same digest, it looks like. So looks like I can start the experiment back at like 4,000, 4,300. Yeah, so let me restart that, and you should at least see it pick up faster. And then I'm not going to look at this continuously, because even though it's faster than my previous voltage glitching experiment, it's still going to take a while. So let's get this going again, and then work on the other project on the desk here. I think 8 repeats might be a little overkill. I'm having it repeat each glitching experiment so that I can be sure I cover all these clock cycles without having to be sure each individual glitch works 100%, which is not really achievable. I really don't know that these glitch parameters are going to be effective. 10 clock cycles. Yeah. I'm going to change these slightly. I'm going to increase the repeat count just a little bit to make each individual glitch just a little bit more of itself. You know, it makes the glitches more likely to have an effect. It also makes your time precision a little bit lower. It's probably fine for this experiment, though. going to back up just a little bit so that I retest some of the overlap with the longer repeat count. Let's just start at 3200. Semi-arbitrary parameter tweaking. Alright, then this mostly starts up and operates on its own. So yeah, I've disabled the power traces that it accumulates, because those also use a lot of RAM. But it's still going to be storing the results here. So the first time it runs, and anytime it encounters errors, it's going to try to reset the PLC, which takes like 8 seconds. Oh, I also need to start the clock generator, since there's always a clock hiccup when I restart the chip whisperer, and the PLL does not survive that on my other FPGA. And then that ends up causing this to restart, but that happens automatically. Oh yeah, a small change in that since the last stream where we were working on this project. I just ended up writing a stupid shell script as a wrapper around the Ethernet proxy to keep it working. So that's this keep on proxying script, which really just sits there in a loop, makes sure that all the debuggers are dead, starts them again, and then uses a ping. What this does is if I end up failing 8 pings continuously with 2 seconds in between, then it assumes something's really wrong and it ends up restarting. So this can take a bit of fussing back and forth to get everything actually started. You can see it's still working on getting its legs a little bit. Once it starts, it should go pretty quickly though. Looks like the proxy just restarted again. All these components with their own reset timers that are not communicating with each other means it can take a little while to start. Link is down. Ooh, is that it? That looks like it. Yeah. I think it just ended up doing a bunch of traces and then crashing. So with the higher repeat count, I am going to get more crashes, which is going to slow this down. So that was looking like it was running, but I didn't actually see the glitches on the scope. I do want to make sure that it's actually glitching before I leave this thing running. Oh, there it goes. Yeah, that looks fine. So that is the experiment working at peak efficiency right now, as far as I'm concerned. Yeah, so it does like a little sprint, doing as many requests as it can without rebooting the target, and then when something goes wrong, it reboots. And like that was an example of a glitch that actually just crashed it, and you can tell the power trace is completely different afterwards. So, and like those are not bad. Like if we don't have any of those, it means that the glitches are not effective enough to cause changes that would give us interesting results, probably. But of course, too many of those and the experiment ends up being really annoying. Well, this might be alright. other thing I might want to do is change the step size, because, if I'm glitching out like 15 clock cycles in a row, then I don't know if I necessarily need to step that 15 clock cycles by one at a time, since there's already kind of a random chance where my actual disruption is going to happen inside that run. But a lot of that depends on the actual mechanism of operation here. Like, it's hard to tell whether the interesting glitches are going to result from, from the pulse itself, or from power supply ringing that happens afterwards, or from, like, the particular like capacitive coupling that I end up getting inside the chip when the signals are ringing, like after that very third pulse. There might just be something very specific. And so, without analyzing a particular instance of the glitch actually causing the chip to crash or operate differently, it's hard to tell what that mechanism was. Oh yeah. Sorry to anybody in the YouTube or Twitch chat that are having trouble getting on the Gitter chat, or that don't want it. Oh no. See, Aleph is in the YouTube chat with reduced internet access due to a hurricane in Texas, I think that is. Or was that Australia? Sorry, Oh yeah, Tropical Cyclone Debbie, sorry. They were saying hurricane in USA-ian, but I was confused about whether that was an actual place or just a translation offer. So when I've run these in the past, it's actually been really nice to just leave them on the video recording rig and get time lapses. Since it is really nice to visually see where the glitches actually end up hitting. But I don't think I'm going to tie up the scope and the video rig for that right now. Oh, this is already this channel I want, actually. So I'm going to leave that on the scope for just a sec, but let me show you an example of the last time-lapse video from the same experiment. I think that's what I wanted. So as you can see, this is an earlier experiment. This was really long running too. This is, what is this at? 256x real time. And you can see from all this flickering that the PLC is rebooting, I think, after every experiment. And here are the timestamps. So like, it's only getting like 10 experiments done every minute or something. And then on the scope, you can see a few different things. You can kind of see how stable all these other waveforms are relative to the trigger. So the scope is triggering off of, it's D3 on this one. That's the trigger signal that the FPGA on the iStick board is synthesizing. So it's not always correct, but this is the trigger that everything else ends up assuming. So you can see that the glitch, which in this case is this little sliver right here, is kind of meandering over rightwards very slowly, and it stays stable relative to that trigger. But since this trigger isn't always correct, sometimes you see this extra main loop cycle show up over here. That means that this trigger actually should have been about a millisecond to the right there. And you can also get a sense of how often this glitch just causes it to crash by looking at the instances of the power waveform just completely changing after the glitch spike happens. You can also sometimes on these views, you can actually see weird events happen in real time. Like if it sends, So like the thing we're looking for is a glitch that causes it to send back a big chunk of binary data that includes parts of its firmware. And so when that does happen on the on the video recording, you could see potentially some clues about what alternate code path it took based on what happened to the power waveform. All right. Is that still going? Perennial glitching question. Is it still running or is it crashed? Like, how much of this do I have to look at to determine whether it's still running? Yeah. There it goes. So this one seems to be much faster for several reasons. I think a lot of it is that it might be sidestepping some networking communication bugs that I'm hitting. And I still haven't determined whether this is a bug in my setup here or a problem with the GDB Ethernet bridge thing that I'm using. But I just have massive reliability problems with any TCP connection that isn't just downloading something small. So, I haven't determined whether it's yet another just plain old bug in my GDB Ethernet bridge, or whether it's something related to TCP timeouts. But keeping the actual web request short seems to help a lot. I also really decided that, well, okay, maybe this is worth investigating. Oops. So, let's see if I can actually open up the web page for this thing. Don't think that will affect my experiment too much. I've got to relearn what all the buttons are. I didn't actually change the button layouts. It's just that things kind of look different enough that it's screwing up my muscle memory. Okay, so here I am just trying to load the web page on here, which will, of course, not work too well when it's rebooting. Maybe doing this at the same time as the glitching experiment is not going to demonstrate my point especially well. Maybe I don't want to stop the glitching experiment just to demonstrate that, but if I can... There's so many moving parts in this experiment. This thing where the Ethernet bridge occasionally dies is pretty annoying. I've also been kind of on the verge of trying to go to a setup where I don't have to underclock the target, which would remove the need for this Ethernet bridge, and it would just make the experiments faster. Right now I'm underclocking it to make it easier to generate a glitch at a particular clock cycle. But I have some faster H-bridge drivers that I wanted to try using. So, I mean, that would be maybe an opportunity to go a lot faster. It just also means backtracking a bit, since I'd want to test that other H-bridge driver on something that isn't this PLC. So I'd want to go back to the kind of known firmware device that I can run tests on without having to worry so much about breaking it. Okay, well, I think I'm going to try to leave this alone for a second, switch gears to the other experiment, which might involve stealing the Oscilloscope, because I kind of want to see this other experiment on the nice Oscilloscope at this point. So, this experiment is the working PLC with the voltage glitching. This experiment is the non-working PLC, which I bricked somehow during an earlier voltage glitching experiment. We still don't really understand the mechanism of the bricking. It seems like either, well, the two theories so far are either an on-chip peripheral that's needed for normal operation isn't working due to hardware damage, or it's some kind of non-volatile memory overwrite within the chip. So I know that it isn't due to anything external to the chip, just, I mean, I guess I haven't tried like swapping chips on these two boards, but I've ruled out all of the external devices I know about on here, which would include things like the real-time clock, the off-chip SPI flash, there's some magnetic NVRAM on here that's used for storing like runtime parameters for the PLC program. But in this particular bricked state, it's not accessing any of that before it just sits there. So it's acting like it could be a bootloader, but we don't really know for sure whether it's a separate bootloader or just the normal program just not getting very far. But so far, all the signs are pointing to it probably being a bootloader. One of the most interesting revelations recently, I think, was taking this setup, which, well, so maybe back up slightly. This setup is an SD card emulator. So when we found that this thing was bricked, I went through and just looked at any opportunities for talking to it. So it wasn't responding over Ethernet, it didn't seem to be using the serial port, it didn't seem to, you know, we already checked the debug interface a while ago and that's been disabled. And didn't seem like any good opportunities for getting into it through the serial devices of any sort. The only communication that seemed to be happening in this bricked state, it initializes the LCD and sends it, you know, initialization commands, turns on its power supply, and sends it a blank screen. Sometimes it's not blank. Sometimes the LCD powers on and it's garbage, but usually it's blank. So it might be sending uninitialized memory. It might be sending something that's been easy to glitch, but it's probably trying to clear the screen. And then it initializes the SD card, reads the master boot record, reads the beginning of the FAT, looks for a particular file name, and then we use this setup to brute force what file name it's looking for. So this thing is another little sub-project that I've ended up putting on GitHub called FlipsyFat. That is running on this left board, which is a Papilio Pro FPGA. So this is a system on chip that pretends to be an SD card, and then you can run experiments on it that, you know, flip through different file names or let you hex edit file contents in real time, that kind of stuff. So previously used that to determine the file name. It is upbm.bin, which doesn't seem to be out there on the internet or anything. So knowing the file name doesn't really help us that much on its own, but it lets us go to the next step, which is, well, now can we give it the file that it's looking for? So that's what I'm kind of up against now, is if there's something that looks like a bootloader, looks like it's reading a file, I now have an opportunity to give it something that there's a high probability that it's just going to run or try to program into flash memory. So if I can keep using this pattern of looking for a side channel that lets me figure out how to give it what it's looking for, and then doing that, then can I sort of wiggle my way to a place where it's actually loading code on my behalf. And part of what makes this especially exciting now is that it looks like this particular file is also something that the PLC looks for in normal operation. So I tried just taking this rig set up to present this upbm file, and then I plugged that into the other PLC, and it does the same thing. And then furthermore, it also, it looks like it's initializing the SD card twice and then reading it using two different libraries. So, man, very easily distracted by the chat when something new comes up. I was like, what is that thumbnail? Is that this stream? Maybe that's another stream. I think that's I think that is this stream, which is a bit of inception. Yeah. What was I talking about? This is like glitching me through the chat. I'm pretty easy to glitch. So at this point, we can get to the point where it's definitely reading the content of this other file. It's definitely kind of doing this other thing that seems separate from the normal application load process. Wherever it gets to the stopping point, you know, whether it reads the whole root directory and doesn't see the file it's looking for, or whether it starts reading that upbm thing and then it doesn't see whatever header it's looking for in there. After that, then the real PLC that's still working proceeds to boot up, and you know, it does a bunch of other things, including rereading the MBR, rereading the beginning of the partition. So that kind of points toward it being a bootloader and then a separate app, which are running on the same hardware but built with different code bases. So the main application doesn't really make any assumptions about what state the bootloader has left things in, and it is probably using, you know, a somewhat different SD card stack to, or at least a somewhat different file system implementation. So the next thing I'm looking for really is when it gets to that point where it's given up on upbm.bin and everything there and goes back to the main application. On the real PLC that's still working, I can eventually start to see it doing other things like talking to external devices and writing other stuff to the display and turning on Ethernet. On the one that's bricked, I need to find a side channel that lets me see when it's given up on that file, so then I can look for small timing differences, and you know, and then I can find out, well, what can I change in that particular sector that causes it to take a little bit longer to tell me that my sector is bad. So yeah, as US Water Rockets is saying in chat, so yeah, the unbricked.plc does load the upbm.bin file. And as far as I can tell, it's doing it in the same way too. So it seems like that's an interesting way into perhaps any of these devices. Like, if this is something that just accepts some code and starts running it or programming it into Flash, then, I mean, imagine if it just starts programming this into Flash, then any of these PLCs, you just put a particularly formatted SD card in there and turn it on, and now you've owned it. You can just write anything you want into its firmware memory, potentially. So that's the kind of thing that I'm looking for, that I'm seeing clues that might actually exist in here. So I had this over on my other desk, and I was trying to make some sense out of it using my older oscilloscope. And I think I really just want to take a look at this on the nice oscilloscope. So I think that is the next thing, is to just get this test running and take a look at it using the nicer equipment and to see if we can find a good side channel. If this is just passing on control to... So I guess there's a question of whether the bootloader in the bricked PLC is passing on control to the application and then the application crashes, or whether it's just not passing on control, because that could affect what sorts of side channels we might see. I'm also curious if it's just putting the CPU in any kind of low power mode that we might be able to detect by just looking at the kind of low frequency current consumption, because that might be really relatively easy too. PLC autoplay, yeah. It does seem like there's some kind of autoplay on here. So if there's actually an autoplay, then that could be pretty interesting. That's definitely the kind of feature that, I mean, I don't know. Then I start to think about, well, what does this mean, like, from vendor point of view? I mean, obviously we don't know yet, but like from vendor point of view, like, should you put a firmware update autoplay thing in your device? Well, I mean, once you have physical access, all bets are off anyway. But there's always there's a lot to be said for making drive-by attacks harder, since if you have one of these devices in any kind of public setting, or a setting where you just have to like pick one lock to get access to it, then you still want to make it hard to just permanently rootkit the thing so that it's no longer ever possible to trust the hardware. So it's all about, degrees. Physical access, they're always going to have some way in, but you can make it take long enough or have enough visible side effects that's no longer just a really easy way to compromise important data or your organization's perimeter or whatever without anybody even noticing. I had to like fill the back of this with hot glue just so the front panel would stay in place for a demonstration. Alright, I don't want to take this off the scope because it's interesting, but I will. I'm just going to try to do it without crashing the experiment. That's right. That feeling when you really should have switched to a different virtual desktop, but instead you hit the video switcher. That's what I'm looking for. Let's get the anti-static strap going. Oh, is anyone else having trouble with Gitter? Looks like see Aleph is reporting in the YouTube chat that they're having trouble with Gitter, getting an internal server error. I'm wondering if anybody else is having trouble logging on from Australia. All right, power side channel no longer available. Carefully unplugging all of this from the live system. You win if you unplug ground last. Alright. Alright, well, I'm gonna keep a slight eye on that to make sure it continues going, but I think I'll be able to ignore that experiment and let it run. Yeah, okay. So that one's running. It is currently occupying some computer time, but no longer tying up the Oscilloscope, which is nice. So I think now it's time to unbox the new power supply, because the other thing this is tying up is the power supply. And this power supply is a workhorse. I've had this thing for many years, but I figured that this might be a good time to see if I could get an upgrade from work. So that is what I've done. So now I won't have my Sanrio experiments tying up all my power supplies all the time. Yeah, so as you might see Eston saying in chat, the feeling when the device under test changes behavior due to scope probe parasitic capacitance. That is something that I was really worried about with the probe right on the vCore rail, the blue one, which is a big part of why I wanted the low noise amplifiers on there. Yeah, as far as I can tell, like from the experiments in the last couple days, I had that extra probe on there because I wanted to double check the performance of the amplifier, and that's part of, because I noticed that it wasn't performing especially well right around the glitches. But yeah, having that amplifier just permanently attached and taking the other end of it with you is much better peace of mind, because it's a lot less likely to change the circuit when you unplug this from the scope. I also spent way too long making this cable because I wanted an SMA cable that was a little bit longer than the other ones, and got to learn some of the incorrect ways to do these attachments. These, I guess, are not actually crimps. I tried crimping them, and they didn't really survive the process, and so I ended up soldering. Well, you can see some solder around that shield part, which is probably unnecessary, but mostly solder the center connector and then solder the shield under this piece here. All right, let's get that power supply unboxed. This will be fun. What camera should we use for that? Hey, cat, are you around? Hey, Tuco, are you around? I think Tuco's outside. This should be nice. This will be like my first. Oh, geez. It's like spectrum analyzer. I didn't order a spectrum analyzer. That looks nice, but no, they're just trying to. They're just trying to either get me or my employer to spend a lot more money. That's what they're doing. These look nice. Everybody's got their own name for the process of integrating digital waveforms over time. Digital phosphor oscilloscope. Yeah, anyway. This is what we came for here. Got standard power cord thing. Quick start guide. So yeah, there are a few things that I really like about well, I mean, obviously I haven't used this yet, but I'm looking forward to having a programmable supply in my lab for the first time. It'll be nice enough to have just a nicer quality multi-output power supply, but I'm thinking the programmable outputs should be quite nice for these experiments that seem to every so often need me to go get the device out of latch up. Here's the software. So it comes with a manual and some software. It has a USB connection, which I'm assuming I can probably script with Python. Oh, it does have Ethernet. Great. That's handy also. Yeah, currently my scope is not on Ethernet, but I should probably put it on the network, possibly a separate network. I don't know how much I need to worry about security for those devices, but it is tempting to put my test equipment on a dedicated network. Cables, USB, and some alligators. Got spade lugs and bananas. Oh yeah. Man, mail time is especially great when it's like really nice test equipment that that people send you. It's pretty awesome. Yeah, so I'm looking forward to having this piece of the shop running at a somewhat higher level of both quality and automation. Oh, that's great. Now I just need to know where to put it. I think it can go underneath the other power supply. It's got to verify voltage before operating. Whoa, check that. It has a, maybe I should get this under the desk camera. So it's got that verify line voltage before using thing on the bottom. But then check out the AC selector. It has 4 different voltage settings, so you can get 100 volts, 120, 220, 230, which I guess probably makes a decent amount of difference when you've got a transformer with this many taps and you're dealing with this many watts. Neat. Well, let's try to get this on the desk so we can actually use it. I wonder if it'll fit over here. That's not what I wanted. That's the button. Just catching up on chat a little bit. Siglent PSU, yeah. Yeah, definitely, I think this is a big upgrade from what I've got, for sure. So this is maybe gonna have to move. This is my little button thingy for switching channels on the stream. I might also just put the Siglent under that one. This up while the experiment is running. This one gets a little warm, but this heatsink on the back is really oversized, I think. Well, I guess I should do the voltage selector thing that it says before I put it back there. Pretty sure we're closer to 120 than 100 volts around here. I guess I could take a look though. Where do I have a kilowatt? Got one of these, and I'm just looking for somewhere to plug it in. I guess I'll just plug it in down here. I'll just use my little monster of 1-foot extension cords for this. Volts, 110, smack in the middle. Well, I suspect 120. It's probably more like it. But that is interesting that it's giving me the choice between 100 and 120. Oh, nice. Just looking at the chat and Kyle mentioning a power supply that you can tell it into, look around at the voltages on port 555. Oh, yeah. There's probably too much unauthenticated test equipment out there. Is that still connected? I think we're good. That wire is a little tight. Tower of power supplies here. Never quite sure what to do with the giant thick cord for the surface mount rework tool. This thing is always in the way on my desk. These I might have to put all the way up here. Oh no. Automatically. This might need some adjustment, but it's probably pretty close to doing all right. Sweet. Tower of power supplies over there. Oh yeah, Chris is pointing out in chat that the 100 volt setting is probably for Japan. That makes sense. Oh man, so I have a lot of equipment rearranging to do. Some of you might know I got this pile of rack-related stuff recently, which is intended to replace this IKEA rack substitute that I have going on. So there's going to be a lot of reorganizing for that. I think I also need to just completely change which UPS is powering what. So now I'm thinking like, okay, both the lab power supplies. Oh geez, are these even on a UPS? If so, which UPS? At least having the rack, you know, it's like the rack itself is a nice interface boundary. Like I can make sure that anything going in or out of the rack at least conforms to something reasonable. Oh, that cord is pretty short. Almost plug it in. Okay, plugged in. Yay! Siglant. noticing that, I don't know, it comes with 2 sets of probes, which like would make sense if they were giving you 2 different kinds of probes or a probe for each of the 2 outputs. But it seems like they've mixed those 2, and I have 2 different kinds of probes for each of the 2 different outputs. I've got one with spade lugs, one with banana blended plugs. It's also really nice to have one with a higher output voltage range. I mean, I guess I have some really cheapo switching power supplies from eBay that go up to like 40 volts, but I really only use those for stuff that I don't really mind overvolting or subjecting to a lot of noise. So I think right now I want to use these 2 outputs for the 12-volt output for my amplifier, and then the like 8-volt output for the actual device. I'm getting a bunch of viewing angle from all the way over there. Oh yeah, good advice from Dr. Toon about test lead quality. Yeah, I've definitely found some of the just worst wire on test leads. You can get so much better quality just by like buying the parts yourself to make sure that the parts themselves are actually worth selling. Oh, this is not quite enough room for the soldering irons. That's definitely going to need to change when I reorganize the stuff with the rack. Alright, soldering iron slightly out of the way. Ooh. Eight volts. Cool. Alright, 8 volts at like 400 milliamps, let's say. 300. And then, oh, is this a touchscreen or not? I always forget. Oh yeah, and then here's the little slide switch that picks 2.5, 3.3, 5 volts for the other output. It's pretty basic, but sometimes you need basic. And I mean, I'm sure I'll be powering a lot of like Raspberry Pis and stuff off of that 5 volts output. So, 2. 12.5 volts. At 200 milliamps. Okay. On. Yay! Cool. I still don't have a place to put this. Maybe my whole soldering enterprise needs to move elsewhere. Or maybe just separate hangouts for the micro soldering and regular tips. Cords. this out next time I use the soldering irons, but right now I'm just trying to get the streaming thing back in place. Alright, this is going to yet again mess up my muscle memory, but at least it's somewhere. Alright, ugh, these leads feel kind of terrible. Both of these are really going to 0.1 inch. I have some banana cable to mini grabbers that are kind of handy for doing this in one place, but I only have one set of those. Hey Tuco, are you still outside? You outside, Tuco? I don't know what the least annoying way of going from 0.1 inch header to like banana plugs would usually be. I guess these male to female jumpers might do the trick, but then I have to still like tape stuff to keep it from shorting out. I also don't have very many male to female jumpers. Most of mine are all female or all male. Hashtag gender problems. There's one set of red and black male and female. Oh, here's a... Just need one more. Sure, blue can mean 12 volts. So. Oh yeah, I definitely, so Dr. Toon says in chat, the PSU looks great, but has that only one jog wheel disease. Yeah, I find that annoying too. Even on like my fancy oscilloscope, I kind of seem like, I feel wishing like it didn't try to multiplex the controls so much. There are a couple of little UI annoyances with that, like, okay, like this thing. That message, anytime cursors are off and you happen to bump the cursor knob, then that thing shows up until you dismiss it or you wait for it to go away. Like, stuff like that. It's like, it's so easy to accidentally hit that knob, and then it's like explaining how this feature works. And like, that might have been useful the first time, maybe. Every other time, it's just annoying. Yeah, so I end up with something like this, which is okay, but then I end up wanting to wrap that positive with some tape so that it doesn't touch anything it shouldn't. Just lightly, something that's easy to take off but will prevent short circuits. Don't worry as much about ground, but maybe I should. All right. So let's turn these off. It is kind of nice having that power supply on-off button. I've also never had a power supply with that feature, which is kind of, I'm going to enjoy that. Okay, so for the 8-volt input, I'm going to hijack this. I was just powering this off of the USB 5 volts, but I think I'd rather give it a nice clean separate power supply if I can. It still has its own, well, so the reason I would care about cleanliness is if I'm trying to do something more serious with the power side channel, in which case it's helpful to have everything that you don't care about as quiet as possible. In this case, there's still a switching regulator on this board, which I might want to get rid of if I go down that route. That is supposed to go over here. Let's not get these two backwards, that would be bad. 12 volts. And this red cable goes to the Oscilloscope. I ended up using my own 50 ohm termination since when you turn this thing on and off, apparently you can get some pretty big voltage spikes at the output of the amplifier. And the built-in 50 ohm termination on this scope does not like that, and it will complain. But if the scope is in high Z mode and you have your own terminator on there, then it doesn't seem to care. Volts. The other thing I want before powering this on is clock. And I'm going to be generating the clock on this FPGA, so I just need to hook this FPGA up to the laptop. This uses the dreaded mini USB connector. And this particular one seems to be pretty bad. I feel like I need to bend this connector down a little bit to make it actually stay. All right. I couldn't tell if it was focus or servo AF or not because oh yeah, hey listen, Navi Scope Edition, yes, for sure. Oh yeah, so I haven't actually checked to see how bad the spike is because it usually happens when I'm not looking. But I mean, the amplifier is powered off of 12 volts, so it could be as much as that. That's pretty good. Cable salad is healthy. I think I've seen that somewhere. Don't remember where. All right, we are also going to be doing this part on the laptop. Welcome back, Lappy. Alright, so here's our CentOS VM. And this is, oh, maybe I can make this slightly bigger. Alright, so this is back in FlipsyFat in Linux VM with all the FPGA tools in it. And this edit file experiment does what it says on the tin. It also has the useful traits of handling reset and clock generation for the device under test, which is done in this function here. So if we boot this on the FPGA, then supply power, we should start to get somewhere. Oh, that's right. This had the flashing, which I know somebody in chat before was complaining about the flashing, and I totally agree the flashing is annoying. Maybe I'll just hack this so it doesn't clear the screen in between updates. Can I make this bigger too? Yeah. Okay, so that was the program. The actual screen clearing comes from the way the hex dump does its updates. Oh, or maybe I'm lying. Maybe the clear is in the main program. Oh yeah, this thing, force status. Yeah, so I think my original goal with this was that it would clear the screen only when it was periodically redrawing it, not when it was redrawing it because of keyboard input, which was my solution to a different version of this problem, but they're both hacks, and really I'm just going to take this out entirely and make it not clear the screen. Instead, it's just going to write over stuff, and if there's stuff that it should have cleared that it wouldn't have, then it would just end up staying on the screen as garbage, which we'll probably see a little bit of that. Really, I should just see if I can compile ncurses for this FPGA. If anybody isn't familiar with ncurses, it's like the library you would usually use for doing terminal manipulation kind of stuff in like Linux. Can I clear this with the keyboard? There we go. That's kind of what I wanted, except the next font size up I think is now too big and it causes the flickering to come back because of scrolling. So I think I've got to keep the font there for now. But anyway, that's the experiment again without so much flickering. So, power supply. Can I get this to not be so glary? I mean, the screen is probably going to be blank, but it would be nice to see if it does something. Okay. We still need to put some of those digital probes on the scope, but let's just get the power on. Cool. I think it's working normally. So you can see it resets, and then we're definitely getting some artifacts from not clearing the screen. But a reset, and then this trace reappears. You can also see it's leaving some garbage over here on the screen, but that's fine. It seems like maybe an improvement. This also is not restarting the experiment automatically. I have to manually press capital R, but I think that's fine for now. Yeah, so let's get some stuff on the scope so we can actually trigger on any of this. I think the bare minimum here is going to be just really the latched trigger outputs from the FPGA. We don't even need all of them. I'm just going to plug in like the first, well, I guess I might as well plug in all 8. I was going to be like, I only need the first 5, but it's easy enough to plug in 8 wires. I do need a ground. Ground on there first, and then 7. so hard to actually find the center of these. There we go. 7. Oh, this is also totally off topic, but I've been enjoying the new social network Mastodon, which is basically an instance of GNU Social, which is kind of an open source system for making Twitter-like things. And it's a little bit hard to tell like what the actual difference is that is making this one take off as opposed to earlier incarnations of that, but I think it's a combination of the actual code base for this one being easier to develop on and deploy, and maybe a critical mass of people starting to move off of Twitter because of all the annoying changes they've been making with that lately. So, I don't know, it's been interesting. I don't have any of the, like all the stuff that I have on Twitter right now for these streams is currently not on Mastodon, but I might add stuff like that in the future. If you weren't aware, right now there's a Twitter bot, Scanlime Live. There's also a Twitter bot, Sanrio Labs, and those are the best places to just follow to get updates when these streams actually start. I feel like I need to put this keyboard away so I don't accidentally touch it. That's not the keyboard for the computer I'm actually currently working on. Okay. So I think what we're going to see is, oh, let's actually get all these triggers. Okay, so that's the 8-bit trigger word, which is set by software and then actually output by the hardware when when a particular SD card transfer finishes. So I think D0 is going to be any block, and if I remember right, D4 is going to be the block that we're actually interested in right now. So I'm going to trigger on D4, but we're still going to want to look at the others for context. And hit reset. There we go. So each of those pulses on D0 corresponds with a single block read from the SD card. And in fact, those should correlate with these 5 blocks we're seeing up here. So 5 blocks up here, 5 pulses on D0, those are going to be the same blocks. So now we can start to figure out, what interesting operations might be here in the time domain, and what else could we find that maybe leaks information about those ops. So specifically, I want to know, what happens after the trigger around the time when it decides to stop processing this. So, for example, if you look at the gap between those blocks, it's taking about 10 milliseconds between them. A lot of that is probably the time spent actually sending the data, especially because of the underclock. So the decision point we're looking at is probably really soon after this trigger, definitely less than 10 milliseconds, but probably actually pretty soon after the trigger. We just need to know how to get it out of there. There is what looks like a pretty definite change in the power waveform there. It's not very consistent. This is also when it might be nice to use averaging and just collect some more data first. Oh yeah. I was trying this other experiment on my old oscilloscope and wasn't really getting the information I needed. That certainly looks like it's turning something off, or just like stopping in some kind of busy loop. I'm going to modify this so that it's automatically resetting and I don't have to keep pressing this button. So that would be down here. Many ways to do this, but I'm just going to call reset pulse from well, I don't want to call it from in here because that's inside of an interrupt and reset pulse is going to block. But I want to call it from the main loop after I get to this point. Oh, that's the code I already had for this, so that's not quite what I want. Oh yeah, it is. So this file last read keeps track of the location where we last read from inside the file we're working on. So this doesn't get set from like just reading the MBR or reading the fat header. This only gets set from that actual block we're interested in. And then right after that, on the main loop, we start resetting, which is what we want. So just more like that. Make load, reset the FPGA. All right, let's reset the screen to clear that a little bit. Great, so now you can see it kind of running in a loop. So last read momentarily goes to E00 and then it resets. So the oscilloscope should continue to be averaging right now. Let's look at the broad view first, and then let's take a few averages zoomed way in. I don't know if we're going to see much way out here. I mean, I think we just have so few samples that we're not going to get the... It's like I kind of want both peak detect and averaging sometimes. I want it to detect peaks at one time scale and then average those. What about this time scale? This might be working. Scope. Let me try to track down Tuco while that's collecting averages. Tuco, you out here? were you getting up right as soon as I put the camera on you? That certainly looks like the processor's asleep or in a busy loop, doesn't it? So that's maybe a good sign. Let's look much closer. Oh, am I too close now? Oh no, that shows it pretty clearly. We have about 100 microseconds before it shuts itself off. Let's see if we can see that zoomed in this far. I mean, if this is the only side channel we got, it would be annoying. It'd probably be doable. I would just have to make something that does some averaging and then communicates with the oscilloscope, and I would have to probably use this oscilloscope to do it. Hey, Tuco. Is that just turning right off, or is there anything interesting? I'm kind of curious what the pattern is like there. It's probably just a busy loop. I just want to know if there's something else going on in there that we might be able to notice. I might also get an Oscilloscope probe out and just start poking around while it's doing this. Yellow probe, maybe? Oh, I don't know what, oh, so Dr. Toon was saying, hi, a nice empty box pile. I'm not sure which one you're referring to, because there is like a pile of mostly cardboard recycling near the front door, which is always there. I'm always terrible at taking out the recycling here because it's actually really far away. The pile in the middle of the room is not empty, though. That is all stuff that it needs to be set up. Oh, geez, Tuco. Hey, Tuke. So yeah, that pile over there is rack mount equipment. The boxes on the front are UPS on the right and some shelves on the left. And most of the boxes in the back are for the rack itself. Oh, Tuco. That's not helping. Honey. I don't want to close the terminal, thank you. Hey Duke, I love you, but I don't have any other input devices on my computer. Oh, he is warm. That's interesting. You know, I wonder if that bottom, well, so before I moved it, you might have seen that there was kind of an underlying sinusoidal waveform with some noise, and then there was the stuff that seemed to stop. This might be an example of the stuff that is being generated by the CPU and the stuff that's coming from the switching power supply. It is really tempting to clean up the switching output here. So right now, this is being powered by the onboard switching power supply, but I'm wondering if there's just something easily I can pull off the board so that I can give it an external 3.3 volts. Oh yeah, the front door pile. Yeah, it is a little big. Oh yeah. There's also a question in chat about this thing. This is an old art project I made. It's called Eclipse. I have complicated feelings about it. I'll talk about it sometime when I feel like talking about art. But right now, it's hanging out in my shop. Okay, let's take a look at the power supply section of this. I don't know if there's something I can do to improve this noise situation a little bit. Let's see. Anti-static strip, and power off, and maybe microscope. Cool. Power off. Hey, Tuco, you back for more? Tuco, there are so many delicate experiments running on this table right now. He doesn't care. Are you looking for a good spot to watch the birds, Tuco? Can't quite tell what he's doing. This little experiment kind of taped together so that I can move it as one unit, but it doesn't really work right now. Well, I think this is actually pretty easy to figure out. That looks like, let's look up that ST, is that ST? Oh no, that's TI. 54160, I think that might be the switching controller. Maybe figure out, maybe trace the output from there and see if it goes anywhere interesting. What computer do I want to use? Buck converter. I think I've heard this name before. I don't have very many analog or power supply chips memorized, but this one sounds really familiar. Tuco, you're chirping to the birds. Oh, wow. Are you going to hang out over there in your usual spot? If anything could be called your usual spot. Master of disguise. So 1.5 amps, lots of voltage input, that's fine. Pretty normal buck converter. I just want your pin out. What is that? does pH stand for? Power handling? Usually I see that as SW for switch node. pH, power MOSFET high, I guess? Anyway. I don't think I actually need anything from here, but that was fun. Let's just look at the board. Maybe with the microscope, though. I think the capacitor, the output capacitors are right on the opposite side of the board there. So this capacitor is the input capacitor. You can see that's where I've already been supplying the power so far. And I think this is going to be the output capacitor, so that should be our 3.3 volt node that we care about. And, I mean, there are probably a bunch of ways to do this, but it is tempting to just pull off that inductor. I think I'd rather do that than cut a trace, but I think first I'm going to power this up and just make sure this is 3.3 volts. So, power. What are these? 3.3, 1.7. And that's going to be the switching node. So, I mean, another thing I could do is try to put the switching regulator in shutdown. But it feels like maybe a surer kind of decoupling to just actually remove the inductor. Oh, interesting. Piotr says pH stands for phase for me. That's a good point. I hadn't really thought of it from the perspective of like a power supply that would have many of those, but yeah, I guess that is how you would make a large power supply. And then Len is asking in chat if, Len says you used to use a USB oscope, right? What was it? Was it useful? The USB oscope I've used the most was the Bitscope. I don't know. It was not necessarily a scope that I would recommend anyone else buy. Like there were some things that I liked about the design, but it just ended up being really underpowered, and the scope it's like it has some like custom logic and like a PIC microcontroller and it's mixed signal, which was nice. And it captures into onboard SRAM, but then it has a serial port for reading it out. So I don't know. Unless those have gotten significantly faster, I wouldn't get a bit scope. And I sometimes hear okay things about other scopes. I think Picoscope has made some good ones. I wouldn't really call it an oscilloscope, but if you need something that can analyze digital and analog signals, the analog discovery from analog devices is pretty good. But yeah, in general, USB oscilloscopes are hard because a lot of people sell stuff that is actually not that good, and like it's easier to find a standalone oscilloscope that actually, I think, fulfills basic engineering oscilloscope sorts of functionality than it is to find a USB scope that would do that. I'm still debating between pulling this inductor off or cutting a trace or something, or just disabling the regulator. Getting the pin, there's got to be an enable pin. Yeah. So there's enable. What actual pin is any of this? Pin 3. Pull down below 1.2 to disable, float to enable. So what do they have that connected to? It looks like they have, well, okay, is that 394 resistor also connected to that? Let's buzz that out. I was going to say something based on just that circuit on the right side, but then I noticed there's probably a trace running under the chip. Okay, so that's pin 3, which is our enable. Goes to this test point, which is stabilized by this capacitor, presumably to ground. There's also a pull down. So a pull down actually would disable this. So is this a signal coming from elsewhere maybe? Or is this a pull up? Oops. Right. Let's not be probing around this while it's on. That's bad. Okay. That is ground. Okay. So that is a pull down. That's O1D. What even is that? So, I mean, taking this with the giant grain of salt, since I'm measuring this in circuit, but this is measuring 75K. It could be this is not actually in circuit. I mean, maybe this is actually, I don't know. Let's see what this other thing is and if it's connected. No, that's separate. That is 400K between those two. Is this the top pin, maybe? Yeah, I'm just curious where this goes. Yeah. So that is resistor timing and external clock. Okay, this is for setting the switching frequency. So that's interesting. This pull down would seem to maybe... Oh, it's also connected via this. What is going on over here? that ground? Oh, is this VCC? Oh, maybe this is a resistor divider for enabling it only after a threshold voltage is hit. Is this VN right here? Yeah, that's VN. So that is our 8 volts. That is our input. Okay. So I think if I just desolder this resistor, I will disable the regulator, and then I can power it from its output without worrying too much. Now I need the soldering iron. Let us achieve a soldering iron that is plugged in. I'm just going to move this using 2 soldering irons. Yeah. So I think I'll move this, then I'll verify that it doesn't power on normally, and then I'll add a 3.3 volt wire that I can use to power it. So 3 steps. Oh, the soldering iron's a little dry. Leave that there for later. Alright, nothing fancy. Just make sure that is now effectively grounded. So resistance to VCC is 86K. Oh, this is a pretty... So resistance to ground is like 100K. I think this is a 100K resistor. I think maybe I want a lower value resistor and possibly a short here. Because I think this chip has a built-in pull-up resistor, and while this might disable it, I don't know if it would. Let's just try it. And measure the voltage at that node with this powered on. So power. Amplifier is still drawing like a half a watt, but this is now drawing no power on 8 volts. So maybe this did work. That is 0.07 volts, so this should be pretty completely off at this point. And that is 0 volts. Okay. So let's ditch the 8 volts now and just give this thing 3.3 volts directly. I think I might just solder another one of these, what are those, like 30 gauge? 24 gauge? Yeah. Biggish wires. To this node right here by the capacitor. I think that's where I'm going to be putting in my 3.3. a little bit of solder there. It's like one of those noises, like, is that my noise or is that someone else's noise? My robot's happy. It's probably a noise in someone else's part of the warehouse. Sounds like a big machine. Big machine far away, not little machine close by. I have just like a little bit of this wire. It's nothing special, but it's wire. Tin this end, a little bit of solder. Can I get this microscope angled a bit? I just need longer wires for this stuff. I guess that's the 8 volts that I'm taking away anyway. Just trying to get that somewhere where I can see it a little better. A little bit of burned hot glue, but we're fine. Bleh, hot glue smell. Okay, that'll be better than our noisy voltage regulator. And I guess I'll use that one. The one that has a little bit of a solder blob exposed, but it's not otherwise connected. Normally I would put another ground on here too, but I've already got some quite nice grounds on this board, so I don't think I need any specifically for this. The ground I'm thinking of is on the other power capacitor right next to this. Ah, that's better. Some glue there. Tweezer time. should end up being basically the same 3.3 volts that you have on the top of the chip here. I did make a little bit of an attempt to filter the 3.3 volt power. That's why, so this is a separate 3 volt plane for the processor with its own capacitance and resistor, so a little RC filter. I'm gonna see if just switching power supply out of the circuit though helps more. So, power supply needs to not be on 8 volts now. All right. Oh, amplifier on. 3.3 volts on. Ooh, that seems shorted. I was drawing a little bit of current and hitting the current limit. Let's check for problems here. Oh. 33 ohms to ground? How did that happen? Separate it by this capacitor. Let's see on which side of this the short is. So something's shorting this thing that this new wire I just added to ground. And I need to know what that is so I can power it. Let's go ahead and power off the 12 volts too. Man, the lights on this power supply that tell you which channels are on are really not competing with the sun in here. I might have to figure out if there's a way to make those brighter. Okay. Where's the short little thing? Oh yeah, so sorry, I haven't really been paying attention to chat. I'm trying to figure out where to so this soldering, I'm trying to add a 3.3 volt. Well, I'm modifying this board so that I can run it directly off of 3.3 volts instead of using its built-in DC-DC converter, just to see if I can reduce the noise. But overall, this is the board that I'm doing the SD card file name experiment on. And there, I've got the file name. I just need to figure out what to put in the file. And so for that part of the experiment, I want kind of another side channel oracle that I can use to figure out when it's done examining the file. So far, all I've got is power. And I want to find something different, but right now I'm just on a sub-quest to make the power trace a little bit cleaner. That is weird. Getting negative 26 ohms there. What if I probed through the other direction? Something with this circuit is not resistive. And then 33 ohms. So I'm shorted through a diode, maybe? Maybe that makes sense. I mean, but depending on the switching topology, that can make a lot of sense, even if it's disabled. Maybe I should just take off that inductor. I was trying to do this just by disabling the switching regulator, but I think that it still like, I don't know, I haven't looked at the circuit completely, but it's acting like there's a diode to ground on the output, basically. And that might be totally sensible, given that this is a buck converter. What do I get on this side? So ground. Yeah, 33 ohms. That's ground. Yeah, so that's through this diode. So I can take off the diode or the inductor. I don't know if it matters. I'm also tempted to use the dual-wield soldering iron technique for this. I'm kind of tempted to go for the inductor because I'm not going to put it back on backwards if I need to put it back on. I'm just going to try taking off this inductor by dual-wielding the soldering irons. Oh, that iron on the right is having some trouble. It just doesn't have as nice a tip on it. Maybe let's swap these. It's running away. It's certainly one of the more thermally challenging parts to take off. I just figured it would be harder to destroy than a diode. I think this is also just giving my old WES51 some trouble with the amount of heat. Okay, maybe let's try the diode. Oh, this feels like it's so close. I think I might have figured out how to hold it so I can actually apply heat and some pressure. kind of want to keep that attached so I don't totally lose it. Alright. Will not be in circuit, but I will not necessarily lose it now. So those are ground. Oh, no, that wasn't what was connecting this. Darn. I guess it's through this chip. I guess I do still have to pull off the inductor. Oh well. So I do have a hot air gun, I just don't necessarily want to heat up this entire area of the board just to pull off this one part if I can avoid it. Just in a trying to do no harm kind of philosophy. I mean, the hot air gun is pretty invasive. It's the sort of thing that is totally necessary a lot of the time, but I try not to use it if I don't have to. I'm just going to try to get a bit more metal over here so I can actually get a good thermal connection. I think I've got a good thermal connection on both sides. Not quite sure, but I feel like I'm grabbing it. Whoops. Sigh. It's easy to stop caring about preserving this inductor though, and I'm tempting to just cut the copper right there. About right now that I start to wonder if it's glued. Well, maybe it is time for hot air. I mean, I'll do that if I have to. I just didn't really want to subject this whole side of the board to it. I mean, it is tempting to cut a trace instead of hot airing the board, since that's a little less likely to damage stuff that I still care about. This just has so much heat sinking. Pop. Hi there, inductor. Alright, I'm done heating this up. This is the dullest X-Acto blade. Okay, do I have any sharper knives? I need to get a new knife blade. Oh yeah, I do miss the binocular scope. It's a thick chunk of wire. Is this working at all? Fine. All right. All right, all right, all right. This inductor's had it. Don't think I need this thing to have its own onboard 3.3 volts anymore. Are we good now? No! What? The short is somewhere else. I'm getting 33 ohms from there to ground. That's ground. Is that the same, the other polarity? It's still reading minus 30 in the other polarity, like there's some active circuit there. Maybe I will try ramping this thing up slowly and see what happens at just like a volt or so. Maybe even just see where the heat's coming from. Okay. So I am ramping up the input voltage. It should be like 0.4 volts right now, so let's see if we're actually seeing that. Ooh, not that. Having bad multimeter luck today. Yeah, 0.032. That is not 0.4. Is that just all cable loss? What have I got at my cable? Oh, or I haven't plugged this in. That would also be a reason for it not to have power. Let's plug this back in. Still 0.40 amps. Now if I measure it... Oh, that's right. I also already took off this side of the capacitor connection. Let's put that back. Because the problem is not as simple as I was hoping it was when I took that off. Power is off. Not the best joint, but it'll be enough for this next test. So I still just have the power supply set to give it 0.4 volts. So I'm going to try plugging that back in. Okay, so now it's drawing like 160 milliamps at 0.4 volts, so there's definitely just a short somewhere. I'm going to turn this down even further to like 0.2, and then let's take a look at where the voltage is going. So now it's drawing 80 milliamps. Point 0.2 up there. 0.2. 0.2 up here also. Point 0.2. Man, where is that 80 milliamps going? I wonder if this would show up on a thermal camera. We could use that method of determining where the shorts are. Gotta take my phone out of this case to use it. RIP inductor, yeah. Wildmania is saying it's time to remove the ferrite part to see what's beneath. I don't know if that's necessary. That was the part that I was having trouble getting off. Yeah. Oh yeah, so Sodium is explaining this quite well. Yeah, the inductor removal was intentional, although I didn't really want to destroy it. That was just after I had given up on desoldering it nicely. And then I was hoping that would fix the short because I thought the short was through the, because I was powering the buck converter through its output, but it looks like it's somewhere else. So I'm just going to see if the thermal camera here will actually give us any clues. Get that on the screen too. Can I use this one? Ooh, I can use that one. It's not optimal, but it's on my hotkeys at least. That's what I wanted. Yes, yes. Fluorone. I think I have to turn it off and then back on. There we go. Oh, that is the shiny ruler. Is that new warmth or old warmth? Yeah, it wants me to recalibrate. Is that something about the LCD or? That is the shiny Ethernet connector. Looks like there's something warmish. Keep in mind also I'm only putting 0.02 watts into this. So maybe for this to show up on the thermal camera, I need to give it a little more juice. I'm going to crank this up to where transistors aren't going to be turning on yet, but at least if there's like a resistive obstruction, I'll be heating it a little bit. So 0.4 volts. Now let's do a half a volt. So a half a volt, now I'm putting a tenth of a watt through this thing. Is it one of these capacitors? I mean, all of that is shiny. What is that? Is that shiny or hot? Looks hot. What is that? That looks like something on the one of these add-ons that I've put on the board. Like that looks like the probing that I've put on top of the SPI flash. That noise is annoying. Which noise? Can't tell if you're talking about an acoustic noise or visual noise. Does look like it's coming from that SPI flash area. Doesn't quite seem to be coming from the flash itself, though. Actually, it seems to be coming from just to the left of the processor. Oh, have I found some conductive debris? Yeah, I think I know where that is on the board. That looks like it's right around that resistor bank next to the processor, like on the right side. And that's an area that I've done a lot of work on, and it seems like something might be able to get stuck there. So let's see if there's some debris in that area. Let's turn the power supply back off. Let's maybe move this a little bit over. I remind myself what orientation this microscope should be in every time I put it in. Looked like it was coming from right in approximately the center of the frame. Oh, is that a piece of something? So this is a really tiny wire. And this is a cat hair, which I can't quite grab because these tweezers are dull. Let's see. use nicer tweezers for the cat out. There's like this stuff over here, which seems very concerning. And then there's... I was curious about this shiny thing right here. It might just be a scrape in the solder mask. I just don't know what kind of conductive debris would give me such an intermittent resistance reading of like positive or negative 20 ohms. I'm measuring between ground on this amplifier board, which should be the same as system ground, and the top of the chip, which should be 3.3. And I was getting like negative 54 ohms. This is also 3.3. Negative 28 ohms. I think that's a diode. That area right there looks really sketchy. That's ground. That's 3.3. Some kind of conductive or almost conductive debris right in that area could definitely be causing the symptoms we're looking at right now. Did that change anything? No. I wonder if there's something I could do with this isopropanol that would be more accurate than the FLIR, like give it just a little bit of current again and watch where the isopropanol dries up first. These are the two, like these two vias could be what the short is between. It's still weird though, it isn't a dead short, it's measuring like here, minus 28 ohms. Super weird. Yeah, just catching up on chat slightly, and it is pretty weird that, like, yeah, for higher impedance circuits, I would certainly imagine, like, flux causing problems, but it would be, like, I'm definitely into the I have no idea what's going on, I'm just trying things kind of phase of this. But yeah, we can break out the FLIR again and see if that helps. Turn on the half a volt again. So it's half a volt at 0.1 watts. And the heat should be right around this area that we're looking at in the microscope. You can see that big cold spot from all the isopropanol. Oh yeah, but then there's a warm spot coming up. I'm trying to move this around to avoid the glare, but it does look like that warm spot is staying where we think it is. It's just really hard to see what it's actually coming from. There's all this stuff in the way. You know, I had another Flare app that might be better than this. There was one that was like, oh, maybe I already deleted it. Yeah, the other app was maybe gonna let me do landscape mode, but that's fine. It's not really a big difference. So it looks to me like it's centered on the right side of that resistor bank. Maybe there's something related to, I don't know, this, oh, that's probably the copper tape being shiny. Just check to see if I see anything on the back side. Huh. What is that? Oh, I don't even know what I'm looking at right now. So that was glare off the back of the LCD. What is this cold spot near the top? That's around where, I think that's just where some isopropanol is pooling up inside the flat flex cable there. It's a homemade flat flex, so I don't think it's actually waterproof. Also, maybe I'm just holding this so close that the two cameras on the sensor aren't really aligning. Yeah, I'm willing to blame all of that on isopropanol in the flat flex. I don't see anything other than that on the back side. Yeah, that looks like a puddle of isopropanol. That is the amplifier being warm. Or possibly just its connector being shiny. The board is still drawing like 1/10 of a watt. I wonder if I can start to see this under the microscope with small amounts of isopropanol. Maybe I should just look for a voltage gradient in that area. Alright, DC volts. So that is 0.6 volts, which is weird because the input is only supposed to be a half a volt. Is that running high at all? Oh. Right, something's going weird here. So the input to this whole thing is supposed to be a half a volt on the power supply, and I'm measuring it with this meter at 0.47, but then I go down here, that's 0.62 volts. Where are we getting 0.62 volts? I mean, are there any other power supplies on this circuit? I mean, the 12 volts is turned off. Oh, I wonder if this is getting back powered through the SD card emulator. Try unplugging that. So I just unplugged the SD card emulator. It's still drawing 0.22 amps at 0.5 volts, but maybe this will explain where that voltage was coming from. Yeah, that's 0.1 volts now. 0.05. So maybe that current draw was actually because this resistor was dissipating the power from the SD card emulator. 0.05. Yeah, because now I've got effectively 0 volts across these. Yeah, I know these resistors are SD card related, actually, now that I'm thinking about it. Okay, so maybe that was a red herring, because we're still drawing 0.1 watts at half a volt. That might not have been the part we were looking for, so maybe back to the thermal camera. Yeah, I mean, the other suggestions in chat are good, like either touching it or using liquid, and I've been thinking about those. It's just, I'm also trying to be very gentle on this, so I'm giving it very little power right now. Maybe I can use a pointer in the field of view here to actually see what that is. Maybe a plastic spudger. Maybe a pointy plastic spudger. Do I have one of those? Oh, here's some plastic tweezers. Oh, that diode. It's the diode. I don't know why this diode is shorting, but I think, oh man, it must be a Schottky diode. I think that's the diode that this circuit uses to, I think that's how it powers the real-time clock off of either the incoming 3.3 or the battery or the supercapacitor backup. This thing. Oh, that's not the camera. Yeah, let's just measure voltages on this. I forget what kind of diode package this is, but maybe I'll measure continuity with the power supply off first. Okay, power off, continuity. I think this is the 3.3 volt in down there, but one of these is I think we're going to find a connection to the new 3.3 volt rail we added. Okay, that's just this. So yeah, this diode, I think it isn't in circuit for the CPU, it just is here because, hey train, this happens to be where I tapped the 3.3 volts for the CPU here. But, you know, I think I can just unsolder this because it's not necessary right now. I just would like to know why it's shorting. So one of these should be the main 3.3 volt rail, which is this one. Another one should go to the backup battery, and then another should go to the real-time clock. The backup battery is on the other circuit board that is not connected. I can try to just test all the pins on the header and see if one of those go there, but maybe it's easier to find the one that leads to the real-time clock first. I'm going to test this one across all the pins on the RTC, and then the other one. I think that's the RTC. And that would be the backup battery. So is the RTC like shorted or something? I don't think so. But whatever, I don't need the RTC, and I think I'm just going to remove this diode as the next step. I'd still kind of like to know what's going on, but I think regardless of what's happening, removing this diode is next. Don't know if I'm going to take this off without destroying the diode. I think I just broke this lead. I need there to be less solder on there. That is kind of a giant mess. Just trying to get this off. Yeah, I don't know whether this is a not enough temperature or not enough flux problem. You really don't have to add much flux with this quick braid because it has flux built in. This is also a power plane connection. Oh, that's a nice puddle. That's maybe more than I actually wanted. Usually it's easy not to overdo it with the flux pen, but There's an exception for everything. Okay. I think I have that out of the way at least. I can get this transistor, or not transistor, get this dual diode package off. I don't think this is surviving. May have soldered the X-Acto knife tip briefly to the pad. Just come with me, little diode. It'll be fine. So I am going to solder that resistor back on. I just want to take this opportunity to do some resistance tests. And maybe we even try turning the power on a little bit. So Kyle is saying, I'm really tempted to just jokingly say that dumping a few amps into the short will clear it right up. Well, that's not too far from what I'm doing. I mean, I was giving it a little current and looking for the heat, but I'm trying to be gentle with this board. If this wasn't so hard to replace, though, then I would be pretty tempted to take that strategy. It's just hard to get more of these boards. Well, none of these are shorted, apparently. So I wonder if this was a conductive debris problem, because there is a ground, like right here, this ground strip right here. That isn't ground. But if this were shorted to ground, then we would be getting behavior very much like what we were just seeing. So let's also try turning the power on. Ooh, oh, maybe not. Still 0.1 watts. Let's leave that on and check voltages. .2 volts. It's interesting. That's like half of our. So the supply is a half a volt right now, and this is a quarter volt, which is interesting. That's a half a volt. That's 2.5 volts. What? Oh, you know, this FPGA is probably trying to drive reset high. Can I verify that? No, reset's just floating up to half a volt. That's definitely 2.5 volts. Where is that coming from? I shouldn't be having voltages that high in my system. I wonder if it's coming from the clock? Oh yeah, I do have a clock coming in probably. Let's try just powering off this whole FPGA. Yeah, that must have been the clock. Okay. So we're getting a little bit of MCU back-powered by clock, but that's fine. That's unrelated to the current problem. So this is now half a volt, and we're still getting the 0.1 watt draw. So is it something? Is it maybe one of these capacitors failing? That's also half a volt. These capacitors, though, are powered through this resistor normally, so like the current shouldn't be passing through there. I mean, maybe it is time to turn up the current. So take another look with the flare camera, but there might come a time where I just give it a little more current and then see what gets hot. Oh, nice. Just reading the chat. Yeah, Piotr says the best debug approach I saw my mentor doing was to attach a large battery to the circuit and see how far the traces were bending under the solder stop to see where the short between the two traces was. Yeah. Oh, nice. And then K. Temkin has definitely fixed internal shorts in ICs by burning through them, which, yeah, definitely harder to get inside an IC than it is to get something like that to happen externally. Let's get the flare going again. Please attach and turn it on. I know. So that's a reflection. I don't know, that's still showing kind of in that same area. Maybe it isn't related to the SD card. Is that conductive debris? Is that conductive debris? I don't know, I thought I saw something with my naked eye that now it doesn't look real. I think I was just seeing the edge of that glue puddle. What is... Let's turn that off for a moment. Really looks like it's coming from just this general area. Like it could be either the resistor, this capacitor, or something around this ground plane atrocity right here. Ooh, which does have a little bit of moving room to it. How much can I move that? But now I'm also wondering if these capacitors failed for some reason. I could try taking off these capacitors. I don't think they're necessary, although these capacitors and those... I mean, I could try just unseparating the whole ground, or 3v3 plane here, like undoing this mess that I made earlier. I'd like to not have to do all that if it's just a simple piece of conductive debris, though. Alright, power on again. Same results. Now I'm briefly wondering, like, oh, is it like on top of the chip. Oh, or is it the MRAM chip? Is the MRAM shorted out somehow? Oh, this actually looks like it might be the whole MRAM chip. Oh, sorry, I thought I was on this screen. Oh yeah, a good question. Can I disable the overlay image? I have not seen an option to do that, but I can put a piece of tape over the camera. Oh, hello. I think I can turn off that other soldering iron too, which is apparently warm. Yeah, so I can put a piece of tape over there, and now we just get the thermal image. So easy to warm him up. Oh yeah, Kyle's saying in chat, this is why we need macro scale circuits. This is reminding me of this kid's game, Robot Odyssey, that I used to really like. And it had these giant circuits you could walk around inside of, and you could summon this toolbox that would have these like logic gates that were as big as you, and you could carry them around and assemble them. And then you could see the electricity propagate through the gates as they would turn red and white. I think the camera's working. So can I recalibrate this first? Okay, what do we actually have here? This is network, which is shiny. That is definitely looking like the MRAM chip. Which, luckily, we don't need that. In its current state, it is not talking to any of those external devices. Could this have something to do with the tiny wires I added to it? Like this little one below it? Where does that one go? I think that's write protect. Yeah. Let's just check voltages on these pins, all of them that we can get to. So we've still got half a volt going into the whole system. Half a volt, 0.2 volts. Half a volt. We should probably find a pin out so I at least know which one's power and ground. 0.13. Half a volt. Alright, let's get a data sheet for this. What is this again? Can we clean that a little so it's easier to read? I was going to grab a scrubby thing, but I didn't see one handy, and maybe I can read this anyway. Nope. Let's grab a scrubby thing. Either way. Nice. MR2SH10 CDF, something or other. I think I have a data sheet for this handy already, but I don't know where I put it, so it's probably easier just to Google it. Not that. Oh, that's probably 25. Yeah. For a second, I thought that was the world's largest memory. And I'm like, well, no, probably isn't. This chip probably is not the world's largest memory chip. It's probably actually pretty little. So this is the fancy magnetic memory stuff, magnetoresistive. 1 megabit. So the one that is closest to my glue mess over there is VDD. Let's see if there's an easy way to separate that from the power to turn this off and see if we can get it to stop drawing current for some reason. .5 volts. Where is that even coming from? Oh, and where's ground? Just for completeness. Ground is pin 4. Which is indeed ground. Don't know what would have... Like, if this is actually a short inside the MRAM, I don't know what would have caused that. But there are, of course, other explanations for this, too. I'm finding myself looking at the other PLC to see where this goes, because it's a little annoying to find it on this PLC. Pardon the handheld microscope work. Straight down through a via. All right. Let's look for a similar setup over here. There might just be a via that I can cut on the bottom side to disable the MRAM. Power off again. Yeah, nothing interesting under that. I'm assuming it just goes to a plane, and I'm gonna have to do something really inaccessible up here to unpower it. That's annoying. I can get in there to cut the trace. I might even be able to put it back if I need to. The clock glitching. Oh yeah. Kyle says at this point I'd be tempted just to lift that little microcontroller or lift the UC off the board and put it on something of my own creation. Yeah. I mean, I've thought about doing that on many occasions. For most of my experiments, that would have required reverse engineering a bunch of the I/O stuff because it pretty quickly hits like an I/O error watchdog reset when you try to power, like even just powering this board up without the board underneath it, it causes that. So I assume that to get this microcontroller running on its own, I would need to figure out a bunch of the stuff on this board and replicate it. For this particular experiment with the bootloader, it seems to need very little of this stuff, so that's not as big of a concern, but I was also briefly misinterpreting your comment about the MRAM chip and like, oh yeah, I should throw this MRAM onto its own board and play with it. But then, oops, that was the end of the knife. That's going to end up inside my foot at some point, isn't it? I'm trying to make sure there's a nice clear path of non-conductivity between these two, like a fire break. But I'm also trying to be relatively gentle and to leave enough room to reconnect it if I need to. Can we flush away some of that debris? Alright, I think I'm going to give it the 0.5 volt again and see what happens. That was it. No short. The short is either under or inside the MRAM chip. So somehow I killed the MRAM. Great. Yeah, I wonder if that was at all related to the original thing that bricked this board. But as far as I can tell, in this mode, it never even tries to communicate with the MRAM, so I don't see how that would be related. There is a bunch of Tuco's additions to this board. Man, it would suck to have a cat with conductive fur. That would make electronics really hard. Working on them and even just being around them, stuff would just break. Okay, let's see if I can just make sure there's nothing else about to cause problems and then actually give this thing 3.3 volts. I do want to put this clock signal back on. Alright, FPGA is going. That did not reset and clear. That's better. Okay, so it looks ready. Our trace buffer is empty. Alright. Plug the rest of the stuff back in. I'm going to try turning on the amplifier. Amplifier is on, drawing a 0.5 watt. So now I'm going to turn the main power supply off, and then I'm going to try giving it 3.3 volts. limited to like 200 milliamps. Cool, 10 milliamps. Can I reset it? Okay, well, somewhere in between success and failure. It's drawing the right amount of power, but I'm not seeing any indication that this is responding. What else is missing? Another scope probe would help with this situation. Kyle says, I'm astounded at the bravery of anyone willing to walk around an electronics lab barefoot. I don't know if it's bravery, I think it's more stubbornness. I think I just really like walking around barefoot, and I just keep doing so even after I keep hurting myself. I'm gonna trade this low impedance ground probe for the terrible alligator clip, just for some convenience while I'm probing around. Oh! I think I'm still missing 3.3 volts on the CPU. I think that might be part of the problem here. I don't think we put this back. Yeah, let's put that back. That might help. All right, power's off. I was trying to just solder bridge it, but I think I might need to push it a little too. There we go. That is a little RC filter that I added pretty early on in this experiment to try to clean up the power for the CPU. Probably not necessary now, but it's there, and it would be more work to remove it than I feel like. Okay, does that help? 20 milliamps now. I still don't see this coming up. Oh. It was just reading the... It was reading part of the file system for just a second there. Okay, well, let's get the scope hooked up. This is kind of working, but also kind of not working. also still in averaging mode. Let's turn that off for a moment. Trigger on any SD card block reads. Yeah, that's not working. Why isn't that working? I wonder if we can see any of the usual signs of this thing rebooting. Oh, yeah, the DSLR. I don't necessarily always need continuous recordings with this thing. It's just, this is my usual source of footage for stuff that I edit together later. And so it's nice to have a good sampling of me doing a lot of different things on the DSLR. That's a lot of where the editing goes. Well, my next inkling here is to oh, did I lose an SD card connection here? I think this is supposed to be ground. Oh, I think that wire might have been the issue. It looks like I'm getting proper resets now. Okay, I think I just needed a ground that had lost its way on the SD card cable. That's better. Because like none of the stuff that I just did should have been like massively breaking stuff. I was trying to just clean up the power trace. Now that's finally better. So we're back to the triggers down there. So every D0 pulse is one block read from the SD card. The others are stuff that I added in software. I forget what they are. I think D1 has to do with the directory entries. And yeah, so I think the first two, I think these reads are in order. The master boot record, then the fat header, then the root directory, then the file allocation table, and then the actual file contents. So I think D0 is just any block. D1 is root directory block. D3 is file block. And then D4 is one that I added specifically to just trigger this experiment. So if this is all correct, then I want to be triggering on D4, and I want to be looking at the power waveform from right after that. And I hope the power waveform is still good. I think it might be. I think we can go back to averaging. Let's see what that does. I'm going to let it collect a few averages. David's Math says, pretty sure electronics engineers are supposed to wear socks and sandals. Yeah, maybe. I've got to make sure not to wear just socks around here, because that's actually pretty dangerous. The floor gets pretty slippery and it's very hard. So... Just noticing a comment from Suddenly Corporeal back in the YouTube chat. So, saying, this is doing no harm, presumably presumably that was relating to how I didn't want to use the hot air, because that would heat up everything on the board. Yeah, I mean, in general, I'm trying to do as little harm as possible to this board, but like, in particular, the inductor and this MRAM chip are for subsystems that I really don't care about right now. Oh, a sign of age. Socks on the floor equals dangerous instead of fun. I don't know if it's age so much as just having fallen enough. Actually, I've got one of those hover scooters, which I haven't used in a while because I need to take it, open it up again and give it another once over on the electronics and the mechanics. It started squeaking a little bit, so I think I might at least need to lubricate the bearings. But if you have one of those, I would definitely advise to check out the electronics pretty frequently, especially before you charge it. But anyway, so far it's been an interesting electronics toy and fun to kind of tool around in the shop with, but it's really bad to fall off of on concrete. I just really banged up my tailbone a couple of times, and it was usually because I'd be riding that thing and then would start to lose my balance and then would try to catch myself, and then because I'm wearing socks, it would just result in me falling. So socks, definitely not good for that sort of experience. So I think I was probably zoomed in a little too far. Let me try this a little bit from maybe here. It looks like it was better. We're still getting a little bit of that lower frequency stuff when the CPU appears to be stopped, but I think that was an improvement. That does look like an abrupt change right when the CPU turns off, or it goes into an infinite loop, or whatever it's doing. Let's make sure we have a good cursor. So cursor 1 is at our trigger. Cursor 2, I'm going to say this is probably about what time we're looking for right now. So just to recap what we're doing here, this is a really zoomed in trace of the noise that the CPU leaves on its power rails as it runs. So basically it correlates with the high frequency components of the CPU's current usage. So it's kind of a way of peeking into what it's doing without actually having any signals that it's left for us. A side channel, if you would. And so in particular, that trigger is an event we know about. The trigger that's a block read where it's reading some data out of a file and then making some decisions based on that data. And in this case, it's deciding that our data is terrible and it doesn't want anything to do with it, and so it's leaving us alone. So we want an oracle that can tell us as soon as possible when it's decided to leave us alone so that we can go start another experiment. And best thing that we can have is a really low jitter oracle that tells us, no, this is exactly when it's given up on you, so we can look at small differences in how long it takes to give up on us in order to quickly find a block that passes whatever tests it's subjecting us to. So what I really want to do is find some external signal that gives us the same timing as this, and then the subsequent experiment will present this device with different file system blocks, and then we expect to see a difference in this time. So having an easy way to measure it that doesn't involve sitting around with an oscilloscope and averaging a bunch of samples would be really nice. But There is always the option of just automating exactly what I'm doing right now by running some software that talks to the scope. Oh, I also want to respond to David's comment in chat, who says, I always find socks collect all the detritus on my floor, so I end up walking around with the sharp stuff that makes itself known at every step. Yeah, I have that problem too with socks. And it seems like it's a little bit better when you're using socks that are thicker, because then there's more cushioning for the detritus that it catches. But then the thicker socks are also the ones that are more dangerous to slip around in the shop. Looking for a good ground here. You know, it might just be time to start poking around every I/O pin on the processor and see if any of them do something at around this time. Is that scope still averaging? I guess it's just converged. Doesn't seem to be changing much now. Let's turn off averaging back away on this a little bit so we get a faster response. Okay, so same time, different data. Can we get this with the Oscilloscope? Yeah, little oscilloscope, big microscope. Alright, so just a control experiment, maybe. I don't know if I have a good control experiment. I mean, let's try 3.3 as a control experiment, maybe. Alright, I mean, that shows that the probe is working, but about it. So the thing I'm looking for is really any voltage difference we can use. So if a pin switches from tri-state to non-tri-state, if it, if there's some small disturbance because of an on-chip peripheral changing state, like anything we can get really. A lot of stuff is going to be easier than pulling this out of the power waveform. Whoa. Is that just the SD card clock? I mean, an oracle that tells us when the SD card transaction is complete is not super useful. I think that's just the SD card clock. What was that? I think that's just SD card chip select. It's power and ground. Something else. More SD card related stuff. I'm looking for stuff around that second trigger. Stuff that happens around that first trigger is interesting, but not actually useful because it's redundant. Huh. That one is probably just ground, I'm just noticing that it seems to get a little bit furry after the transaction ends. Same there. Oh, maybe that's chip select. Did I just short it out? I think I just shorted out this pin. It's fine. Test is still showing good results. Running low on stuff I could access right over there. Plastic tweezers. Oh, I wonder if I can see anything on the clock output. Like if the processor was shutting off the clock. So here's the clock input, like you'd expect. Doesn't appear to shut off the clock. So far, my bets are on this thing is going into a busy loop, but not actually turning off any peripherals. This may be a good time to mention that the only peripheral I've even seen it talking to in this mode, other than the SD card, is the LCD. So that is maybe another area where it might be doing something. What is that? That's like less than a volt. find the LCD stuff on this right side. Oh yeah, good suggestion from Kyle in chat. Possibly it needs the system clock anyways, and so it's just turning down the internal PLL frequency. And then I would see the emissions change. Yeah, I still don't know whether it's even trying to power off any hardware or if it's just sitting in a loop. Like, you know, if I was an engineer who didn't necessarily care that much about all the tiny little failure modes in this bootloader, I can imagine just throwing like an assert statement or something that goes into a busy loop. There's like this long landing period where, like, when I'm not using the binocular microscope, I don't really know how far away things are. I also have to keep watching the trigger indicator flash because I don't want to like probe something but then not actually wait for the scope to update. Another furry ground. Oh yeah, the other thing I was experimenting with, which we might try if this doesn't pan out, is to use a B-field probe, which is to say looking at the magnetic emanations rather than the power supply. And I don't have a lot of experience with that so far, but I've mostly just been trying making my own little B-field probes and using another one of these same low-noise RF amplifiers. That would still have a lot of the same problems as looking at the voltage rails, but it's possible the signal will be cleaner. Oh, what's that? Oh, that's my clock. Right, I'm way back up here again. Hello, clock. Nice to see you again. The other thing that might be easy to do relative to the power trace itself is to look at DC current consumption, which is really a similar problem to power trace, but because the frequencies are so different, like, maybe I try measuring that. Oh, I already have a 3.3 volt shunt resistor in this one. I should just try measuring that. I mean, this is certainly looking unsuccessful so far. We've got one more side of this chip to test. That wire is so in the way. Where are my non-conductive solutions for wires that are in the way? I guess I was thinking of plastic tweezers, but I could use a stick too. Jared asks, are the furry grounds coming from the circuit or from the cat hair on the circuit? Oh, good question. Maybe both. Although, I don't think the cat hair is actually involved in the ground conductivity path. This wire has gone a little bit stiff near the end. These pins up here are a great combination of difficult to get to and really unlikely to show me anything good. What is that? That's probably core voltage. These kind of tend to fall slowly when I probe them, which is weird. Anyway, I think that shows that there's nothing interesting. Yeah, so the second pin in, I was noticing that there seems to be something that charges that up. Let me get my ground back. Hard to reproduce. Yeah, maybe it charges up slowly over time. Oh wait, now sodium is saying, wait, is that a coincidence or did that one pin go back high, the same as the second trigger? That would be nice if that was it. Do you know which pin that was? It certainly wasn't one that I saw. Oh, and then Ben is asking, is the other unit still glitching off to the side? It looks like it. We can check out the VM to see if it's still working. Yep, that's still going. It doesn't have the scope connected, but the chip whisperer is still recording the results, and the Raspberry Pi is still logging all the Ethernet packets. Oh, second pin from the right. Oh, okay. Let me check this one. Oh, always so many wires. That's the second pin from the right. So just to check, the experiment here is still running, so it is still reading the files and giving me the triggers. If the experiment wasn't still running, I guess the scope wouldn't be triggering at all. Not seeing anything good. Just out of curiosity, anything I broke out on JTAG changing? I mean, they wouldn't be changing processor state or anything like that. Yeah, let's take a look at that resistor. I want to see the resistor. I might even try to probe both sides of the resistor, but first let's just try the side closest to the CPU. I also kind of want a better ground for this, but I'm going to be lazy for the probing at first, and then I'll probably have to improve this. So that would be this giant resistor here. This enormous quarter-watt resistor. Experiment is still running. Huh. Maybe yellow and blue. Let's try probing the other end of the resistor. I might just need a better probing strategy though, because this probing strategy is kind of awful. Like, I don't have a real differential probe, but I've been thinking about either getting or making one. Probably making one because they're really expensive to buy. Oh, okay, cool. From Sodium in chat, the one with the signal that went high was the 8th in from the left. Let's take a look at that before we get too far here. don't want Y cursors. It's fine. Oh, looks like it goes over here. Experiment is still good, but that is steady state. Let's check its neighbors. 5. Well, thanks for rechecking. That was definitely worth going back and looking at. I don't think it's here, but I'm glad we looked for it. Oh, 8th in from the left, sorry. Left is another direction. Okay. Thank you. Oh. Oh! That would be one of the signal lines for the real-time clock, which is currently disabled, but maybe it's trying to disable it or something. Let's try to get that from up here. Yeah, so these look like they're idling high, but let's try checking their neighbors. These 2 pins on the left are still doing that weird thing where they kind of hold a voltage and then discharge. Pins. These might just be floating inputs then, or analog inputs. I don't know what that one is, but it doesn't look important either. Yeah. All right, let's get 2 probes on that resistor. Wipe all the flux off. How's your nap? Tuko, you smell like cat food. I'm just probing each side of this shunt resistor that's powering the CPU. And can I just use subtraction and AC coupling? So this would be blue minus yellow. I don't think this is going to work super well because the subtraction happens like after these end up like on the display buffer in the scope. It's not going to be especially high resolution. Well, okay, first maybe let's look at these individually. So blue is input, yellow is output. They're both scaled the same on the scope. Man, so blue is just the 3.3 volt rail that is supposed to be stable here. What? Okay, maybe I can get some of the information I want by DC subtraction of these two. Can I do that? DC subtraction, low bandwidth limit. Oh, and then I'm always wondering, like, how do I scale the math operation? It's this one, right? Trying to do all this DC coupled, and now I've got to find the offsets for these signals that are way out there. Where is it now? multimeter. What is my actual voltage here? I mean, it should be 3.3, but I just want to know precisely what is the actual voltage I'm dealing with here. 3.28. That's as far as I can go in with these probes, but it's DC coupled now, and it does look like we have some current draw disappearing right there. I don't know if the math is going to help us here. Yeah, maybe I need a differential probe for this. Or maybe I can even make a little op-amp circuit that would work out. Because I do really want to sense the difference between these, and the math operation in the scope I don't think is going to give me the calculation I want fast enough. Oh. Sodium has an image. Let me see if I can get that up on the bigger screen. Yawn, yawn, yawn. That looks like my probe was slipping. That looks like a really nice coincidence, though. That does look like the pin going off to the real-time clock I2C bus, doesn't it? Yeah, I think I was just slipping with the probe, but that does look mighty coincidental. So the blue side is the system 3.3 volt rail. The yellow side is next to the CPU. Partly what is weirding me out here is that it looks like there's more noise on the system 3.3 volt rail when the CPU isn't doing much. It's a little weird. I really thought I saw, so like here you can kind of see what looks like a step function in the yellow where it looks like it's entering a lower power state. I'm wondering if I can isolate that. Like maybe if I kind of low pass filter this a lot, actually. Yeah, that looks useful. So it's not going to be the fastest response, but I don't know, like latency is not an issue here. If we can really precisely locate that moment in time, it doesn't need to be low latency. But just a plain old low pass filter is also going to make it hard to notice exactly when we want to. I mean, you can see that slope. Like imagine trying to trigger on that slope. It's not going to get a really decisive edge. We're going to have to kind of pick a point. Interesting. Oh man, I think I might need to take a brief restroom break. I'll think about what to do next, and in the meantime, you can enjoy my cat. As always. I guess he's right down here. He should have been in frame the whole time. Differential probe, because I really want to know the current consumption with high bandwidth, and this is really seeming like I need to make a probe. Well, maybe one thing to try before that is to try the B-field probe, since that at least would be pretty good at filtering out this power supply noise. B-field probe box. Hey Tuco, do you know where the B-field probe box went? Here it is. It's actually right over here because I thought I was going to use it. So this is intended not to measure the power rails directly, but to measure them indirectly by picking up magnetic field changes from right next to the chip. A couple of different versions of this that I was working on. I ended up making one with like a 10 millihenry inductor, which is probably not very sensitive at high frequencies, but picks up audio pretty well. This one is basically a little pancake coil. It is a single loop of the coax's interior wire. And I just encased the whole thing in shape lock plastic to make it a little easier to handle. And then this one that's on there is similar, but it's like 2.5 turns instead of 1 turn, and it's encased in hot glue instead of shape lock plastic, but also pretty similar. It's like a ball of hot glue around some wire and a spiral. So I might try this one first. These are designed to have a 9-volt battery power them, and then their output is just 50 ohm coax, same as this other amplifier. Hey Tuco, you hanging out? Volt battery, where are you? Ah, there they are. Okay, this will be replacing the red trace. It might be about time to wrap up the stream and think about additional ideas. I'll certainly take a look at how the other experiment's going before I leave this, though. It is on. Is that really that low noise? Okay, I'm like really cranking this thing up. Well, there's a lot of stuff in there that is not going away when the CPU changes modes. But it does seem like it's pretty easy to tell the difference between those two modes. And that's not even really close to the CPU. Let me try this other probe. I think Tuco's hearing the noises of kids playing in the hallway. This is the amplifier without the battery plugged in. This is the amplifier with the battery plugged in. What was that? Oh, that's the one-turn coil. Maybe put that under the board. Other side is not really free either. Oh. Well, that's nice. Jeez. Oh, Tuco, don't chew on my HDMI cable. I mean, that would still need some additional filtering or detection work, but that does seem to have the signal I'm looking for in it. Nice from Dr. Toon. Tuco has very high gain directional ears, like those long distance microwave horns. Well, whatever I do, I think this involves more probing. So just to recap and collect thoughts and all that. So this is still on the bricked PLC, where by bricked, I think now we mean it's stuck in this bootloader, which is actually still pretty interesting to us because all the devices pass through it still. Poor electronics. Did somebody figure out how to make fonts huge? Oh geez, Tuco, don't climb around in there. Oh geez. Tuco. It is really time to put this equipment in a rack, isn't it? That is a rack mount audio interface that needs to be in a rack. Are you coming out, Tuco? Oh, I might end the stream soon so that I can save some energy for doing other projects a little bit later, but I think I either need to build or buy a differential probe, and I might also want to continue experimenting with the B-field stuff. But having a differential probe across having a probe which is extremely differential to my needs for it to be differential, yeah, I would like to be able to measure the current going through that resistor. I have a clamp-on Oscilloscope current probe, but it's probably way too low frequency for this. But yeah, so what are our differential probe options? I feel like the two things that I know about are, oh, Tuco, don't eat that either. Don't eat that. That's a power cable. It's only like 20 volts, but don't eat it. No, no, don't eat that. Tuco. So the options I know about are just like outright buying one, which I think is really expensive. I mean, I could check, but last I looked, they were really expensive. Also, as far as frequency, no. Like, I assume if I actually wanted a brand name Keysight probe, that would be probably at least $1,000. Oh, what are you doing now, Tuco? I mean, the thing is, like, getting a nice differential probe. Whoa, what is this? This looks like a logic analyzer probe. I mean, I should probably own something like this eventually. But it is also tempting just to buy some chips, like some instrumentation amplifiers, and make little, like, kind of like what I've done with this setup, where I just have like little boards that I can stick onto my device under test. It'd be kind of nice to have a differential probe like that. Yeah, see, this is probably what I'd be into if I were buying this. Whew. Yeah, that's a lot of money. Probably really nice, though. Yeah, the other option, though, is just to shop for chips instead of for complete test equipment. instrumentation amplifiers. Differential and instrumentation. And then we can start narrowing things down to stuff that works for the kinds of frequencies we're interested in. So this is the gain bandwidth product. So as far as gain, I don't know how much gain we necessarily need. So we can start assuming that the gain is potentially close to unity, but at the very least we need, some small number above 1 times the actual bandwidth we want to deal with. So let's say, just for starters, let's pick anything above, like between 200 megahertz and like 2.8 gigahertz. Fine, 10 gigahertz, let's go all the way to the top. Whoa, I just went backward by accident. Oh, Tuco, how did you get in there? Tuco, speaking of probes, that's where I keep my probes, and not cats, just probes. Love you, Tuco. And now he's behind the scope. There's a little bit of cat there, if you zoom in and see it. Hey cat, welcome back. So, $1,200 differential probes and instrumentation amplifiers. That's right, we were on here. Let's simplify this a little bit. Oh, just checking up on chat here. Would it not work to use a Hall sensor connected to the scope? A Hall sensor. I think that's how so I've got this other pretty inexpensive clamp-on current probe, which I think uses a Hall sensor, but it's really low bandwidth. Low battery. So yeah, I've got something like this, which I think would use a Hall sensor. AC/DC current clamp from Handtech. What is this even rated for? So it needs a new battery, and it doesn't say the frequency rating on here, but I'm pretty sure this was under 50 megahertz. Maybe under 100, but just replacing the battery. So, I mean, you can probably guess based on how enormous this thing is that it probably is not meant for tiny wires with tiny signals, but I'm curious now. Oscilloscope. Oscilloscope. Okay, I don't think we need the blue anymore. 1 millivolt, 10 milliamps. That is the higher gain scale that this has. Anything I could clip this on? Maybe just to start out with the input 5 volt rail. That is blue. Well, I guess we've got some DC. We are measuring direct current. It's not really picking up any meaningful differences over the execution of this test run. It might be useful to try putting this thing through its paces. Like, I mean, it was picking up that DC current. Like, you can tell that, well, it didn't really zero itself entirely. I'm pretty sure this is a Hall effect sensor. There are some other experiments we could do to determine that. Oh yeah, you can see the lower current when it goes into reset. We are in high resolution mode. I think if you low pass filtered that, you'd see a little bit of a drop off, but it's pretty noisy. And that is the clamp-on Handtech probe, which is probably much more useful at much lower frequencies than this. Well, laptop. Tuco took your power cable. He just wanted a nom on it for himself. Alright, so we have a lot of choices. Oh, we haven't actually narrowed this down at all yet. I thought I had selected gain bandwidth product, but I think Tuco, or I think I had accidentally swiped back in the UI and cleared this. So 200 megahertz plus, we're looking for some nice parts. And in stock, 557 parts. Minus 3 dB bandwidth. Let's try sorting by descending gain bandwidth product and then look and see where they get cheap. So we've got some stuff all the way at like 18 gigahertz. I did actually want to turn off these sidebars. I'm not really using them right now. These are how much? Where's the price? Oh, here's the price. So these are 18 gigahertz and like $7 each, which I'm sure you need a lot more to make a functioning 18 gigahertz probe. But just for some perspective, like the actual parts they use to make a really nice probe probably aren't that expensive. It just comes from the really careful design and making sure that everything passes through it without, without any distortion that is not really meticulously documented. So I don't think bandwidth of the actual part is going to really be a concern. But where's our prices? So these are op amps. So I'm not quite sure what kind of amplifier we want, but probably an instrumentation amplifier. These are current feedback amplifiers. I guess none of these are listed as instrumentation amplifiers, just differential. I don't actually know what the difference is when you're talking about an amplifier. But anyway, let's limit this to just differential mode then. And dual 10 gigahertz. So gain bandwidth product, I don't even need to look at gain bandwidth product that is more than like 3 gigahertz or so. What is going on there? Just powered it off. Power on. Yeah, this is running. Okay, I think the 120 milliamps is normal, maybe. I don't know, man. It's certainly possible there's another chip on here that's on its way out. It is consistently doing this kind of reset now, though. So yeah, I don't know if this much current usage is normal. This is a little bit higher than I expected, but it doesn't seem to obviously be too much. But we've got this running still. So it is powering on and talking to the SD card. It's alive. It's just acting weird. Huh. Alright, well, I'm going to turn off the power to that for a sec. And the amplifier. And let's just shop for instrumentation amplifiers for a bit. Oh wow, just catching up on chat, so is it not just dumping flash or RAM to the LCD? It would be funny if it was random bit to flash. It would be really funny. My two guesses for what might be happening is it might be clocking out a bunch of bytes while leaving the pin floating. It does look a lot like uninitialized RAM though. My primary theory for that is that it's uninitialized RAM, which is usually but not entirely always zeroed. But yeah, that is still a bit of a mystery. I'm not quite sure what's going on there. And now I'm a little concerned about the current consumption. Because 130 milliamps seems kind of much for this. Yeah, I guess while we're here, let's look at the other experiment. It's up here. Is it? Looks alright. It is currently recovering from an error, but it looks like recently it's been doing alright. Still recovering. Oh, good cat. He's in a good spot there. There we go. After, yeah, now it's going slow again, see? Maybe this is a good opportunity to clear the output table again. Oh, geez, there's so many more yaks to shave, because it's like, this experiment is fine, but it'd be nice if it was running faster. Making it run faster likely involves either fixing a lot of stuff in Chip Whisperer or just not using Chip Whisperer. And I don't even know which of those is less bad right now. Oh, Jarrett is just asking in chat what a noise was, but I think there's too much chat delay for that to work unless it's something that I notice also. There's a lot of weird noises around here. There's the buzz that I can think of off the top of my head is there's like a loading dock. Like I'm next door to a FedEx facility and they have a bunch of loading docks that I think make that noise, but I don't know if that's the one you were talking about. So I'm going to check this and start it just like I did before. So we're up to 5600-ish. I don't see any greens. Let's just make sure that all of these are identical by sorting them. This doesn't look like it's close. Like, part of what's concerning me about this is that I'm not getting any corrupted results yet. And I don't know whether that's because my parameters are not close or because my offset is not close. So I would like to finish exhaustively searching this particular parameter set across all the offsets I care about. But I'm not really holding out a lot of hope that it's going to work at this point. I'm thinking I'm probably going to need to go mess with the parameters. And a lot of this is pointing back to maybe having to backtrack to working on the eval board again instead of the actual PLC, because if I want to change the actual glitching setup, then I would like to test that on a board that is easier to replace first. Well, both easier to replace and easier to develop conclusive tests for. I don't know. There's a lot of options here. I'm just thinking, like, it's been a while since I saw a good glitching result from this particular board where, well, I don't think I have from this particular board. I think the good results I was getting before were before I bricked it. And I'm still kind of trying to get back to the point I was at in terms of the actual glitch outputs from before I switched boards. So it might just be there's something I have to do to tune this setup for this particular processor. Because I tuned it for the eval kit, and then without a ton of tuning, I got it working on the other processor, but maybe I just need to change the parameters. And so to do that, I have to come up with, well, what else am I holding constant? So if I have some HTTP thing that I'm glitching, I need to pick an offset or a small range of offsets, and then within there try to find parameters that give me an expected sort of unusual result. But yeah, that's all a bunch of backtracking, I think. And these are all the same. So let's get this started again. 5600. This keyboard. color scheme is so bad. Can I unbatify this color scheme from the terminal? That's a little easier. Okay. I think maybe that was just intending to have a white background. So, start this a little later. I think that's all I wanted to change right now. These are the parameters that I'm thinking I should be changing soon, but that's a whole other kettle of fish. I just want to reduce the number of things I'm changing simultaneously so that I know what to change next if I get any good results. The reset steps. Oh yeah, restarting Chip Whisper probably means I lost my PLL. I really need to make that automatically restart. One of many, many yaks here. And this should start automatically. Yay. That's better. That's what we wanted. Okay, I'll let that run for a bit more. But yeah, that one, I feel like we're just floating at sea and we don't quite know which direction land is. Like I've got some inklings. Oh, why do we still have a Oscilloscope trace? I thought I disabled that to save memory. It says trace format is none. Maybe it still takes the traces, it just doesn't save them. I mean, it's possible maybe Chip Whisperer's analog input might be useful for this other experiment, but there are many things that I could use that for. Sometimes even when I don't necessarily care that much about price, like when I'm just building a couple of these, I still look for the cheap parts because that tells me what's actually popular and likely to stick around. Not always, but it's a good starting point. Hey, Tuco. It looks like 3 gigahertz is a pretty achievable thing in these inexpensive price points. Well, not that inexpensive, but something like this, except, yeah. Whew. 6 kilovolts per microsecond. Bias. Wow. 96 milliamps output current. And this is a QFN, which is solderable. Oh, there's a suggestion that I end up picking up rubber packages in at the FedEx center that I live next to. It's funny, when I want to pick up my own packages, the FedEx like retail center that I go to do that is actually further away, because like the distribution hub is across the street and the retail center is like across a couple of other streets the other direction. Fully differential architecture. I assume there are easy ways to use this to drive a single-ended load from a differential input, because that's kind of what I want. I don't know if I want a differential amplifier. I think I might want an instrumentation amplifier. Lots of test circuits. There's the application circuits. Single-ended differential, differential to differential. But I want differential to single-ended, which might not be something this can do. Yeah, let's look specifically at instrumentation amplifiers. I think differential amplifiers are not as useful for this. Now, what do we have as far as bandwidths? Oh, geez, these only go up to 35 megahertz? Huh. Maybe we need to do some research. This might just be where I start having to use different techniques, because maybe instrumentation amplifier is not really a thing at these speeds. Oh, what is this? Is this like a reference scope probe? Maybe it is. Yeah, this looks nice. So these are just regular op amps, and this is set up as the subtraction, an inverting amplifier, and I'm spacing out what this particular topology is called, but yeah, it's subtracting the minus from the plus. And I think this is another gain stage. Oh, probably also for impedance matching. Oh, AC coupled inputs. This is cute. Can I get these? Oh, what are these parts like? LTC 62, 66, 68? Yeah, that must be 68. And I guess that's dual. Oh. This is the eval board. Maybe maybe this is an old part. Oh, or I just couldn't find it with the -10 suffix here. I assumed that was a speed grade or something. Oops. Where did that page I was just at go? Is this it? Did I drag that out? I think I just closed that window. I'm not really sure how. I think that's the one we want. Oh yeah, there's like another couple of letters between the part number and the speed grade on DigiKey apparently. These are $4 and not in stock. This is $8 and in stock. Oh, Tuco's over here. I'm so bad at following him around when I'm working. It's almost like we need a robot to do that job. Okay, so now maybe the step I'm at is, this seems like a good architecture. I wonder if somebody just sells a kit that it does this so that I don't have to get all the parts and make the board myself. And is this somebody else's blog post going down this path here? Yeah, this is basically where I'm at. It's like, I just have this one signal that I kind of need a differential probe for, but geez, they're expensive. Can I make one? Yeah. 1 volt peak to peak, 50 ohm. Sure. I don't know if I want mine to be attenuated though, because I'm still looking for some gain. Yeah, and this is an instrumentation amplifier made from discrete op amps. Okay. Oh yeah, I was just noticing the chat a little bit, and Sodium is doing a pretty good job on filling folks in. Yeah, this is, so to back up a step, this is for trying to figure out what kind of a file to give the bootloader such that it can continue. So it's been, reading the file system, reading the root directory, and we've been able to make it to this point by looking at small timing differences and how long it takes to give up on what we've given it and go to the next thing. But since now it's kind of the last thing before it goes to sleep or gets stuck in an infinite loop, apparently, we're not finding any external hardware that it touches before that point. So I'm trying to investigate whether it would be feasible to get the side channel I want by looking at the power consumption. And it looks like the data I want is there. And specifically, I think what I want is the power consumption across the 3.3 volts shunt resistor. It's just noisy, and I think I could pick up a pretty good signal if I had a differential probe. And so now I'm at the point where, oh geez, differential probes are expensive. What other options are there? Can I make a differential probe? Yeah, I don't know, this seems okay, but still not quite amazing. I mean, that reduces the capacitance and increases inductance, right? Well, this article continues. That's cool, but what else is there? I'm still kind of curious who else has taken this LTEC 6268 idea and run with it. No. Whoa. No. Kit is not going to mean what I think it means here. What is this? Oh, this is... I think this is just a tip. I don't think this is actually a differential amplifier. Yeah. Man, that stuff is so expensive. This is probably what I need. If I search for differential probe and megahertz, will at least give stuff that has the frequency specification in the name? Huh. .400 megahertz might be enough. I don't know how happy the Tektronix probes are at working on the Keysight scopes and vice versa, but I would assume they would be, like, at worst I would have to configure some stuff and apply a power supply. Hmm. .500 megahertz, is that a good milestone here? Ooh. Cable cut. Ow. LaCroix. This really looks like the thing that, if I just had infinite money, would be the solution to this problem. look pretty nice. Oh, Robert in chat is suggesting something from Nevena. So this is designed for exactly what I'm using it for. That's pretty cool. It's an ADA 4938. It looks like a differential op amp. Oops. 4938. An ADC driver. Looks like this is going to be differential all the way into the ADC, which is nice, but hard to connect to my scope. This looks like a cool design, though. This also reminds me that I think Colin O'Flynn has a really simple differential probe that he made for the Chip Whisperer, or at least documented for the Chip Whisperer. Oh yeah, this one. Oh, this is the one I looked at before. Is this going to be fast enough for what I'm doing? 200 megahertz, maybe. I mean, this is not quite as nice as what I would like, but might be enough. And so this looks like it's probably pretty inexpensive to build. AD8129. Huh. Differential receiver amplifier. That's what I wanted. This is not an instrumentation amplifier. You know, I think the term instrumentation amplifier might imply like really good DC characteristics. And I don't really care about DC. I mean, DC would be nice, but I'm not going to put in the extra effort to make DC really good, because I don't really care about it. Applications, high-speed instrumentation amps. Thanks. I guess I can't just search for instrumentation amplifier in DigiKey and get what I want, but it still might be a useful term. Well, this might be a good direction. I might want to get the parts for this and make one. Is there a repo with all the latest designs for this? Is this the new wiki? Okay, this is the new wiki. The old wiki still shows up pretty prominently in all the Google results. I was hoping this had a link to the repository. Well, this is related. This is the low noise amplifier. I was thinking about making one of these, but I ended up finding those little LNA boards from eBay instead. Ah, diff probe. There's a new version as of 10 months ago. Interesting. I don't think I have anything that'll open Excel spreadsheets on here. I think I already have this checked out. Tools, diff probe. Oh, there's a Papilio target. That's interesting. I want to make one of these. I'm just looking at what the difference is between the simple version and the regular diff probe is. I think this file is just Eagle specific stuff. I don't think there's actually design in there. Don't know what's going on with that zip file either. But whatever, we have Eagle files and we have an Excel file. How do I open an Excel file? Can numbers import these? I don't want to do any of that, just open this. Trapped by the first run wizard. Now I've got several copies of it. Nice. Oh, cool. Everything except the SMA is available from DigiKey. And I think I already have the SMAs. I can mill the PCB. I think mostly we just want to make sure this chip is in stock. This is like what the entire thing revolves around. Yeah, they aren't even expensive. I should get a few of these, because I'm sure I'll be able to make use of them. Alright, well I think that might be a strategy. So I think where we are now is I've got a pretty good idea that current consumption at some frequency, oh geez, Kyle says, "Oh goodness, my parrots have decided I don't get to watch." That sounds fun though. I've never had a bird in my life for that much, but the birds that I've seen indirectly through friends have been really nice. Parrot sounds like a really nice pet. One is sitting on the keyboard, the other is trying to deep clean my pores. Aww. So let's see. 2 experiments here. One of them, oh, guess that worked. Thanks for not clogging, finally. Maybe I should go over there and swap that out. Having some clogging problems with this printer, but I had a few theories, kept trying things, kept not being it. I guess either I got lucky or I finally fixed it. Anyway. So, slight recap since we're hitting the end here. So we've got these 2 experiments. One of them is still voltage glitching away. If we take a look at that, we should see it continue to make progress. I don't have a lot of confidence that this is actually going to hit a useful glitch, because I think the glitches are not actually, I don't think the shape of the pulses is necessarily optimized well enough for this board. So I think I might have to go back and tweak that some more. But I'm kind of torn about whether to stop this experiment and do that, or just to let this run some more. And I think since it's about time to wrap up for the night, I'll at least let this run overnight. Then on here we've got the semi-bricked PLC, which, as we've established, the bricked PLC and the non-bricked PLC are both looking for this file, this upbm.bin at boot, which I don't see any mention of on the internet, but is probably some kind of firmware update functionality, or kind of recovery bootloader functionality or something. So we've managed to get to the point of figuring out the file name and a little bit of the file structure. We know that it's reading, it's looking for some information that it can, it's looking for something in the very last 512 bytes of the file, and then just from looking at that block of the file, it makes a determination that it doesn't need to see the rest of the file, and then it leaves. So we know that it cares about the file size, and it's using the file size to calculate where this read should come from, but we don't know what it needs after the read. So I can brute force that if I have a side channel that tells me kind of how far it's getting in that decision. So far, I think the best bet for that side channel is actually just the power consumption of the CPU. But yeah, a lot of this stream has been trying to figure out what the methods are for getting that out that actually work for this particular signal and the other constraints of the setup. And it's looking, excuse me, it's looking like power consumption across this shunt resistor, like where I have these 2 probes, is what I want to use. But I think the hiccups are actually coming back. But I think I need an actual differential probe so that I can look. I think ultimately what I'm going to end up needing here is a differential probe, then taking a look at that signal on the scope and just assessing it and seeing what else I need to do to it. and then adding potentially some other filtering, and then maybe a comparator, so that ultimately I would really like to be able to get a digital signal out of this. Even if it's not totally clean, I can use it as a heuristic for whatever kind of FPGA-based test harness I end up wanting to run this on. So I think that's pretty much where we're going. Sean in chat is saying that solder braid is the work of the devil. I kind of like solder braid, but it can be tricky. You definitely need enough heat and enough flux, otherwise it'll just be like, what is this thing that I'm putting on my board? It doesn't seem to do anything. But then you get to the point where you have enough heat and enough flux, and it can just work wonders. So, well, and I kind of like this differential probe. So, and then as far as differential probes, there's a lot of options. Something that's just super well featured and just works in all the cases we care about would be buying the kind of official couple of gigahertz probe from, or like 1.5 gigahertz probe from Keysight, but that would be at least $1,500. That's a lot of money for this experiment. I'm sure I'd use it for a lot of things, but so I think before that I want to try some building my own differential probe options, because that might be more like $20 worth of parts instead of $1,500. So, especially since I've got the circuit board mill here, it'd be nice if I could just spit out probes and related boards whenever I want. So I think my next step here is probably just doing a little bit of shopping, getting the parts necessary to make this probe and possibly a couple of other things that we might need. So I might also look for some op amps that work in these frequency ranges and get some stuff that I can use for filtering. But yeah, so letting this one run for a bit, maybe tweaking the parameters some more. And then on the other experiment, another yak to shave, gotta make something that can give me a trigger signal, some kind of little analog animal for that. So, ooh, also Robert says PCB preheaters are great. I agree. I recently got one. I haven't actually used it a ton, but for the couple of projects I had to use it on, it was really, really indispensable. And it was not expensive. I think it was like $120 from eBay for like an okay but not amazing IR preheater. But yeah, heat gun works if you have nothing else. Alright, well I think we've approximately reached a wrap-up point here, and I'm getting cold, and maybe I should turn on the heater or put on some socks or something. But as we've established, socks in the shop are dangerous. Let's finish up with a little bit of cat here. I'm kind of shivering here, and so it's hard to like really softly touch Tuco. Well, thanks for tuning in, everyone. We will be continuing to do the chat on gitter.im, so if you're interested in chatting, hopefully you found a way to make that work. If you're just joining us now or joining us in the archives, then if you do hang out with us in real time, we have a IM channel if you follow the link on the screen. And yeah, for announcements, there's the Senrio Labs Twitter account. You can follow that and get announcements whenever I work on these glitching projects or anything similar. So until then, happy hacking, everyone. I'll see everyone on the internet. If I can ever stop petting the cat long enough to turn off the stream.